In the quiet hours of the night when the world slows down and your thoughts begin to drift beyond the weight of the day, there is a place where the mind becomes light enough to wander into the universe. A place where the stars feel closer, where time softens, and the questions we ignore during daylight begin to whisper again. Welcome to Theories Before Sleep. Tonight, we're going somewhere deeper than anything you've seen, or dreamed, or imagined. We're travelling back not millions of years, not billions, but to the very beginning of everything, to a moment so ancient that even light itself had not yet been born. Before galaxies, before atoms, before the universe had shape or colour, there was a silence older than time. A darkness so complete that nothing could exist inside it except possibility. And from that darkness came the first light ever created, a glow so soft, so delicate, that it changed the destiny of everything that exists today, including you. For the next few hours, let your mind float freely. Let your breath slow. Let the quiet around you settle gently into place. And if you enjoy these journeys into the deep fabric of the cosmos, these slow, immersive stories that help you drift into sleep, into thought, into wonder. Don't forget to subscribe to Theories Before Sleep and join us every night as we explore the mysteries of existence one theory at a time. Now find a comfortable position, close your eyes if you wish, and imagine the universe when it was still nothing more than a breath of heat in an infinite darkness. Our journey begins long before stars, long before time, long before the world you know. It begins with the very first attempt the universe ever made to shine. Are you ready? Let us go back to the beginning. In the beginning, there was no beginning, no moment to witness, no spark to point at, no place to stand, no air to breathe, no silence to break. There was only a shift, a sudden, impossible rupture in nothingness, so brief, so violent, that calling it an event is almost disrespectful to the scale of what happened. We call it the Big Bang. But to the universe itself, it wasn't a bang, it was a release of pure existence flooding into a space that didn't exist a heartbeat earlier. In less than a trillionth of a second, the universe expanded faster than light, not because it was moving through space, but because space itself was unfolding. Imagine a single grain of dust suddenly becoming larger than a galaxy, then a cluster, then a cosmic web, all before you could blink, before blinking was invented, before invention itself was possible. This first instant was not warm, it was not bright, it was heat. Yes, but heat so intense that the words hot and cold lose their meaning completely. Temperatures soared to levels where matter could not hold form, where particles dissolved faster than they formed, where forces gravity, electromagnetism, the nuclear forces had not yet separated themselves. They were still fused into a single unified power that sculpted everything blindly, as if carving the outline of a world it did not yet understand. As the universe expanded, its energy stretched, and as it stretched, it cooled not gently but violently, like molten iron plunged into icy water. This cooling was not just temperature dropping, it was the universe learning to slow its heartbeat, to replace chaos with structure. During the first fraction of a second, the universe was a storm of raw energy and pressure. But even in this storm, something remarkable began to happen. The first particles flickered into existence, tiny, unstable, appearing and disappearing like sparks in a raging fire, quarks and antiquarks, gluons binding and breaking, neutrinos slipping through the chaos like ghosts with no weight. These were not particles as we understand them today. They were more like intentions, brief hints of the matter that would one day build stars, planets, oceans, and eventually the quiet room where someone is listening to this story before falling asleep. Even at its wildest, the universe was already preparing for everything that would come after. It was shaping the rules, writing the laws, deciding without a voice, without a mind, how reality would behave for the next 13.8 billion years. This was not creation with purpose. It was creation with potential. The potential for atoms, for molecules, for chemistry, consciousness, and the soft moment when a human breath slows as they drift toward rest. But before any of that could happen, the universe needed to survive its own birth. The first second was the most dangerous second in history. The pressure was enormous. Energy density was beyond imagination. A single teaspoon of the early universe would outweigh mountains, planets, entire solar systems. Yet even in this impossible storm, the first patterns began to emerge. Right after the universe crossed the 1 second mark, something subtle shifted. The expansion, still furious, became smoother. The temperature, still terrifying, began falling with more rhythm than chaos. Forces that were once fused now peeled away from each other like threads separating in slow motion. Gravity took its place as a quiet architect, guiding everything with gentle insistence. The strong nuclear force became the sculptor of atomic hearts. The weak force learned to whisper in the background, quiet but essential. And electromagnetism, the force that would one day bring us light, shadows, colour, and the glow of the moon reflected in human eyes, finally stood alone. The universe was cooling, but there was still no light, not yet. Because for light to exist, there must be space for it to travel. And at this stage, the universe was still too dense, too crowded, too hot, too wild. Any photon that tried to move was instantly swallowed, scattered, absorbed, re-emitted, trapped in an endless cycle of collision after collision. Imagine being inside a storm cloud so thick that not a single beam of sunlight can escape. Multiply that density by numbers the mind cannot grasp. That was the early universe, a place with energy everywhere, but direction nowhere. A place where light existed but could not yet shine. Still, something was shifting, slowly, carefully, quietly. The universe was expanding like a deep breath being taken for the very first time. With every stretching moment, the density dropped just a little more. The temperature fell just a little further. The chaos settled just a little faster. The universe was learning to calm down, learning to stabilize, to cool, to prepare itself for the first moment light would escape. But that moment was still far away, hundreds of thousands of years into the future. For now, in this first second, the universe was a furnace of beginnings, a place where space was stretching, matter was blinking into existence, and energy was writing the silent laws of reality. The universe had been born, but it had not yet opened its eyes. This was the darkness before the first dawn. This was creation before the first glow. This was the universe before light. The universe, still in its infancy, stretched outward like a newborn taking its first breath, wide, desperate, unstoppable. Every fraction of a moment brought change, but not the gentle change we witness on Earth. These were cosmic changes, raw and violent, sculpting space itself in ways too large and too fast for any future mind to truly grasp. By the time the universe was a few seconds old, the chaos had begun to settle, only slightly, like waves calming right after a storm, but still enough for the first foundations of reality to emerge. the temperature dropped from unthinkable extremes to merely catastrophic ones. Temperatures began sliding from billions of degrees to hundreds of millions. It was still far too hot for atoms to exist, far too dense for light to travel, far too wild for anything stable. But it was no longer the explosive, frantic universe it had been at the first instant. It was becoming a place where rules mattered, where physics could begin to build, where time moved forward with purpose. In these early seconds, the universe was filled with a thick, blistering soup of particles, protons, neutrons, neutrinos, electrons, and their antimatter counterparts, all smashing into one another with a kind of violence that would vaporize entire worlds. But even amid this storm, something extraordinary began to happen. The forces guiding the universe, once blended in an indistinguishable unity, now separated fully into the four pillars of physics: gravity, the quiet sculptor; electromagnetism, the painter of light; the strong nuclear force, the heart builder; the weak nuclear force, the invisible shaper of transformation. Each force took its role like actors stepping into their first scene unrehearsed, yet perfectly timed. And as the forces took shape, so did the first building blocks of matter. By the 3-minute mark, the universe had cooled enough, just enough for protons and neutrons to bind together. These were the first fragile steps toward atoms. Hydrogen nuclei formed first, then deuterium, then helium. A small amount of lithium too, so rare back then, it was almost an accident. This moment is known today as Big Bang nucleosynthesis, the first attempt by the universe to manufacture matter in bulk. But the universe wasn't ready yet for anything more complex. It was still too hot, still too crowded, still too wild. Electrons, which are essential for completing atoms, could not yet attach themselves to anything. They were moving too fast, crashing too violently. The universe was a factory of beginnings, but every product was unfinished. Still, these early steps mattered, because those simple, bare nucleus atoms, mostly hydrogen, some helium, were the seeds of everything that would follow. The future stars depended on them, galaxies depended on them, life depended on them, you depend on them. Hydrogen, the simplest element, would one day ignite in the cores of stars, breathing light into the cosmos. Helium, formed in the first minutes, would contribute to the birth of those stars. Without these first nuclei, the universe would remain forever dark, cold, and lifeless. But light true, travelling light still had no chance of existing freely, because every inch of the universe was filled with electrons racing at near light speed. A dense fog of charged particles crashing and colliding, blocking any attempt at transparency. This fog is known as the photon baryon plasma, and it was the great jailer of the early universe. Any photon that tried to travel any particle of light that attempted to move in a straight line would instantly scatter off and electron. It was like trying to walk in a blizzard made of fire. Every step was interrupted, every direction lost. Light existed, but light was trapped. Think of billions of lanterns shining underground, with no way for the glow to reach the surface. They burned. They flickered, they radiated, but they were swallowed by the storm around them. The universe was glowing from within, yet outside that glow, everything was darkness. And yet in the background of this violent struggle, something deeper was happening. The universe wasn't simply expanding, it was smoothing, stretching itself evenly, erasing wrinkles, distributing energy across vast, ever-growing distances. The expansion, once violent, became rhythmic. The temperature, once erratic, became predictable. Space cooled from billions of degrees to hundreds of millions, then tens of millions. The change was slow but unstoppable, like a cosmic tide. And as the universe continued to cool, the density dropped. Electrons moved slightly slower. Collisions became slightly less frequent. Little by little, the fog began to thin. Not enough for light to escape, not yet. But enough to reveal a simple truth. The universe was preparing for transparency, preparing for the day when real light would break free, preparing for the moment when darkness would end. But that moment was still hundreds of thousands of years away. For now, in this early era, the universe was more like a heartbeat than a place, pulsing with energy, expanding into nothing, sculpting the laws of physics, allowing the first elements to take their place in the cosmic order. The stars were still far in the future, galaxies nothing more than whispers of possibility, life just a dream folded into the atoms yet to come. But the universe already had the ingredients, the rules, the rhythm, the direction. Something was forming beneath the chaos, a shape, a purpose, a quiet momentum pushing reality forward. The darkness was still absolute, but it was not empty. It was pregnant with light waiting for its moment to be born. The universe had survived its first violent breaths. Now it was learning to grow. As the universe approached its first minutes, then its first hours, a strange contradiction defined everything. It was full of light and yet completely dark. Inside this dense, seething cloud of plasma, photons were being created, endlessly born from collisions, born from reactions, born from the sheer chaotic nature of early matter. But every photon lived as a prisoner. Every attempt at travel was interrupted by a free electron waiting nearby, ready to scatter it back into confusion. The light was everywhere, yet trapped in place. Like a voice screaming in a storm, the message could not escape. This was not the still, peaceful night sky humanity would one day admire. It was a universe still wrapped in a blinding fog, a fog so thick that visibility wasn't measured in meters or kilometers, but in fractions of a millimeter. No photon could travel farther than the width of a human hair before being redirected. And yet this brilliant chaos was necessary. Without this turbulent early time, without this pressure and density, the universe would never have formed the building blocks for stars or galaxies. The chaos was the canvas, the violence was the sculptor, the fog was the cradle. The universe was not ready for freedom, but it was taking the steps that would one day make freedom possible. The longest night in history. As thousands of years passed, the universe continued to expand and temperatures steadily dropped. The cooling was not sudden, not a shock, but a gentle, vast settling of energy, a cosmic exhale that lasted millennia. When the universe cooled from millions of degrees to mere tens of thousands, the collisions inside the plasma became a little less fierce, just a little. Enough for electrons to hesitate for the briefest moment before scattering light again. This was still not transparency, not even close, but it was a sign that transparency was coming. For now, though, the cosmos remained blind. This epoch, stretching from minutes after the Big Bang to hundreds of thousands of years, is sometimes called the Cosmic Dark Age, a name that perfectly captures the truth. The universe was glowing violently within, yet from any distance looked perfectly dark. No stars, no galaxies, no structures, only a vast expanding ocean of hot particles and imprisoned photons. Imagine drifting inside a thick, boiling cloud that stretches in all directions for billions of kilometers. That was the universe, now hot, dense, vibrant, but without a single ray of escaping light. This darkness lasted longer than all of human history, longer than the lifespan of every civilization ever created, longer than the time between the dinosaurs and today. It was the longest night the universe would ever know. And yet inside this darkness, the first seeds of light were waiting, hidden, contained, preparing. For the darkness was not permanent. The universe was already writing the story that would end it, patterns in the chaos. Though everything appeared chaotic, the universe was quietly forming patterns. Not patterns of matter not yet, but patterns of temperature, density and motion. Tiny fluctuations, small differences in temperature, 1 part in 100,000 began to spread across the plasma. These differences were unbelievably small, but they were enough to plant the earliest blueprint of structure. Where the plasma was slightly denser, gravity had a tiny advantage. Those pockets would one day become galaxy clusters. Where it was slightly thinner, expansion won a little more. Those voids would become the great empty regions of space. These tiny imperfections, so small, so fragile, would shape the universe on the largest scales imaginable. Galaxies, stars, nebulae, planets, all were born from the subtle fingerprints the early universe left on its own surface. And those fingerprints were carried by the trapped light itself. When the first photons finally escaped hundreds of thousands of years later, they carried the memory of these early fluctuations. They carried the map of creation. And today, billions of years later, we can still detect that ancient radiation. The uneven glow of the cosmic microwave background is the oldest photograph ever taken, showing the universe before it had stars, before it had shape. A photograph taken in the dark, a photograph of light that had not yet been seen, a universe slowing into order. As more time passed, tens of thousands of years, the expansion of the universe began to shift the balance between matter and radiation. Early on, photons dominated everything. Their energy shaped the growth of the cosmos. But as the universe expanded, their power weakened. Their wavelengths stretched, their energy faded. Matter, on the other hand, grew more significant as temperatures fell. Protons and neutrons stayed massive. Electrons waited for their chance to settle. The universe was transitioning from a radiation-dominated era to a matter-dominated one. This shift was essential. When radiation rules, everything remains smooth and even, spread out like a liquid. But when matter rules, gravity can finally begin to take control. Gravity can pull, gravity can gather, gravity can sculpt. This transition marked the beginning of something profound. The universe was no longer just expanding, it was preparing to build. But before galaxies could form, before stars could ignite, before gravity could fully tighten its grip, one final obstacle had to fall. The fog, the dense, unbreakable cloud of electrons had to disappear. Electrons had to slow down enough, become calm enough to bind to the atomic nuclei formed in the first minutes. Only then would the universe become transparent. Only then would light, after hundreds of thousands of years in captivity, finally break free. Only then would the darkness end. But at this stage of Chapter 1, the universe is still waiting. Quietly, slowly, patiently, it expands, it cools, it settles. The first light ever created, still trapped, still hidden, still unready to shine. But change is coming. The fog is thinning. Order is rising. and the first moment of cosmic clarity draws closer with every passing century. For hundreds of thousands of years, the universe expanded like a slow breath, a vast ocean of particles drifting apart, cooling with each passing moment. It was still dark, still hidden, still wrapped in a fog too dense for light to escape. But beneath that darkness, the universe was slowly, quietly, approaching something monumental, a breaking point, a transformation, a release so profound that it would define the destiny of everything that would ever exist. The universe was approaching the moment light would finally open its eyes. Yet before that moment arrived, something subtle but essential had to happen. Electrons, which had spent ages racing wildly through the plasma, crashing and scattering and blocking every photon, were slowing down. The temperature had dropped from tens of millions of degrees to just a few thousand. To us, a few thousand degrees is unimaginably hot. To the early universe, it was the first breath of calm. As temperatures fell, electrons no longer moved with frantic violence. They drifted more gently, more predictably. They were no longer too energetic to settle into place. For the first time since the universe exploded into existence, they were ready to bond, ready to attach themselves to protons and helium nuclei, ready to form neutral atoms, ready to clear the fog. This process, this long-awaited union, would be called recombination, even though it was the first time atoms had ever formed. The name isn't perfect, but the moment was. Because when electrons and nuclei began to bind together, something beautiful happened. The fog lifted. Not suddenly, not like a curtain being pulled away in an instant, but slowly, gracefully, like dawn spreading across a valley. One by one, the free electrons vanished, not by disappearing, but by settling down, sinking into the embrace of atomic structure, losing their ability to scatter light. And when the electrons calmed, the photons were finally free. After nearly 380,000 years of imprisonment, the first light ever created escaped into the vastness. This was the first dawn the universe had ever seen. A dawn without a sun, a dawn without a horizon, a dawn without eyes to witness it, but a dawn nonetheless. The universe becomes transparent. Imagine you're inside a dense fog so thick that you can see your own hand. Then slowly the fog dissolves not into darkness, but into clarity. Shapes appear. Light spreads. Distance becomes real. That is what the universe went through. Before recombination, every photon travelled no more than a hair's width before crashing into an electron. After recombination, those same photons could travel across the entire universe without interruption. Light had space. Light had freedom. Light had purpose. The universe, once blind, could now see. If an observer had existed in that moment, a mythical witness floating in the calm of early space, they would have seen something extraordinary. Not bright beams, not stars, not galaxies, but a soft, warm glow filling every direction. A uniform, gentle brightness like the ember-like colour that lingers just before sunrise. The whole universe glowed with that colour. Everywhere, evenly. This was the first light. It was not the light of stars. That'd come later. Much later. This was the afterglow of creation itself, the ancient radiation left behind when the universe cooled enough to let light travel freely. And today, 13.8 billion years later, that ancient glow is still around us. It has stretched, cooled, and faded into microwaves, but it is still here. We call it the cosmic microwave background, the oldest surviving light, the universe's first memory, a message from a time when everything was still impossibly young. light begins its endless journey. The photons that escaped during recombination have been travelling ever since. They have never stopped, never slowed, never aged. For billions of years they have crossed the expanding universe, through voids, through future galaxy clusters, through regions that would one day become stars, planets and life. The light that escaped then is still moving now right through you, right through the walls, right through the world. It never went away. It simply grew quieter, colder, softer. In the beginning, that light was bright enough to fill the cosmos. Now it is a faint whisper, a leftover warmth just a few degrees above absolute zero. Yet it still carries information, still carries texture, still carries the fingerprint of the early universe's shape. It is the universe's first photograph, not of stars, not of galaxies, but of possibility. And we creatures who arrived billions of years later can still read it. We can see the density ripples, we can map the early structure, we can trace the beginning of everything that followed. In this light, every galaxy ever born, every star that ever shined, every world that ever formed, every life that ever wondered was already waiting. The universe was still young, too young for stars, but it was no longer blind. Darkness still surrounded everything. But now, that darkness was filled with light on the move, light with direction, light with memory, light with destiny. The first dawn had passed. The first glow had escaped. Now the universe would enter another era, a long, quiet stretch of darkness before the first stars ignited. But this time, the darkness was different. It was not empty. It was not blind. It was not chaotic. It was a fertile darkness, a darkness full of atoms, possibilities, gravity, and promise. A darkness waiting for the first stars to rise, a darkness holding the memory of the first light. Before stars, before atoms, before even protons or neutrons could exist, the universe was nothing but pure energy. Not sunlight, not radiation as we know it, but raw, untamed, shapeless energy, a sea of pressure and heat, where the laws of physics were still deciding what they wanted to be. If Chapter 1 was about the darkness before light, Chapter 2 is about something even deeper. How the universe learned to build the ingredients that would one day make everything we see today. This is the chapter where chaos becomes structure, where energy becomes matter, where the first particles appear, the true ancestors of stars, galaxies, and life. It begins only moments after the Big Bang, but in cosmic time, those moments were enough to change the future forever. The universe, as a furnace of creation. In the first trillionths of a second, temperatures were so impossibly high that matter could not exist, not even for the blink of an eye. Imagine a furnace so hot that anything you place inside instantly turns to vapour. Now imagine a furnace billions of times hotter. That was the early universe. Energy flickered violently like sparks constantly trying to become something, but every attempt at structure was shattered instantly by the surrounding heat. Still, something extraordinary was happening beneath the chaos. Energy and matter were not separate. They were interchangeable, flowing into each other like two halves of the same breath. Wherever energy condensed, particles appeared, and wherever particles collided, they turned back into energy again. Matter was trying to be born again and again, only to be immediately unmade. It was a cosmic heartbeat. Exist, break, exist, break. But with each passing moment, the universe cooled just enough to let matter last a little longer. Not stable yet, not permanent, but longer. and that tiny change was all reality needed to begin taking shape. The birth of quarks and gluons. As the universe reached the 10 microsecond mark, something remarkable occurred. The first particles capable of surviving the heat, even briefly, finally appeared. These were quarks, the fundamental building blocks of all matter that would ever exist. They came in 6 flavours: up, down, charm, strange, top, bottom names that sound playful but hide the depth of the universe's math. At this time, the universe was a thick soup of quarks rushing wildly in every direction, constantly splitting apart and recombining. Holding them together for the very first time was a new force, the strong nuclear force carried by particles called gluons. Gluons did something essential. They kept quarks from escaping one another. They glued them together. They gave structure to the chaos. They made stability possible. Without gluons, nothing solid would ever form. No protons, no atoms, no chemistry, no stars, no people. The strong force was the first whisper of order in a universe still screaming with energy. The first families form. As temperatures fell further, quarks finally slowed enough for something miraculous to happen. They began binding into stable 3-quark structures for the first time in history. These structures were the earliest known families of matter: protons and neutrons, up, down, proton, up, down, neutron. Simple, small, but revolutionary. Once protons and neutrons existed, the universe had its first building blocks, the Lego pieces that would one day form atoms. But at this stage, the universe was still too hot for atoms themselves to exist, too chaotic for electrons to settle, too dense for anything to hold its shape for long. Still, the ingredients were ready. The universe was preparing for chemistry before chemistry existed, preparing for light before light was free, preparing for stars before the darkness even understood what a star was. The role of neutrinos, the first escape artists. Not all particles were trapped in this fiery ocean. Some tiny ghost-like, almost massless, escaped the chaos entirely. These were neutrinos, particles so light, so subtle, that they passed through the early universe without being slowed, stopped, or scattered. They hardly interacted with anything. They hardly cared what the universe was made of. They slipped through the plasma like shadows through smoke. While photons were imprisoned, neutrinos were free. Billions upon billions of neutrinos formed in the first seconds are still travelling today, passing through your body this moment without leaving a trace. They carry the earliest memory of the universe, first second a memory older than light itself. If the cosmic microwave background is the universe's first photograph, the cosmic neutrino background is its first diary entry. We cannot see it, but it is there, a record of a time when the universe was nothing but energy, trying desperately to become matter. Matter versus antimatter, the great cosmic duel. But the universe faced another challenge, one that nearly ended everything before it had even begun. For every particle that existed, a mirror particle existed as well, matter and antimatter. Same mass, same behaviour, but opposite charge. And when a particle met its antimatter twin, they annihilated each other in a burst of pure energy. In the early universe, quarks and antiquarks collided endlessly, a storm of creation and destruction so intense it nearly cancelled reality itself. But then something strange happened. Something tiny, something unbalanced, something that defied perfect symmetry. For every billion antimatter particles, there were 1 billion plus 1 matter particles. Only one extra. One lonely survivor in every billion annihilations. That tiny imbalance, that impossibly small excess of matter is the reason anything exists at all. It is the reason stars exist, the reason galaxies formed, the reason planets emerged, the reason life appeared, the reason you are listening now. Had the universe been perfectly symmetrical, all matter and antimatter would have annihilated, leaving behind nothing but cold, empty radiation. But it wasn't a perfect. It was slightly uneven, slightly flawed, slightly biased in favour of existence. And that flaw, that cosmic asymmetry, allowed the universe to survive, allowed reality to continue, allowed the future to happen. At this stage, in the first minutes and hours after the Big Bang, the universe was still far from stable. But the pieces were forming, the ingredients were gathering, the rules were solidifying. Chapter 1 gave us the darkness. Chapter 2 is giving us the ingredients. And soon those ingredients will become something extraordinary. By the time the universe was a few minutes old, the wild chaos of its birth had begun to settle, not peacefully, not gently, but with a slow cosmic discipline forming out of the turbulence. Temperatures once beyond comprehension dropped to levels where protons and neutrons could finally hold together without being ripped apart by the storm around them. But the universe was still a furnace, still bright, still hot, still dense enough to crush any attempt at stability into dust. Yet among the wreckage of colliding particles, something extraordinary occurred. The universe began building. It built simply at first only what it could, only what the conditions allowed, only what could survive the fires of creation. Those earliest constructions would become the most important structures in cosmic history. Big Bang nucleosynthesis. The universe's first attempt at chemistry. Around the 3-minute mark, the temperature dipped to about 1 billion degrees, horrifyingly hot by human standards, but soft compared to the first second of existence. At this temperature, protons and neutrons, no longer torn apart instantly, could lock together into the first primitive nuclei. Hydrogen appeared first, the simplest element in existence. One proton, sometimes one proton, one neutron, deuterium. A microscopic, delicate nucleus, yet the entire future of the universe depended on it. Then, as the temperature continued to fall, helium-3 formed, helium-4 formed, a trace of lithium, a whisper of beryllium, and then nothing more. The universe wanted to build, but it was still too hot to build anything complex. It didn't have the right balance of density, temperature, or time. The first atoms would not form, not yet. Electrons were still too energetic to attach to anything, and so, for now, the universe was filled with bare, nuclei-naked hearts of future atoms, waiting for their moment. These early elements were simple, almost childlike, but they would become the raw material for everything else. Hydrogen, the fuel of stars. Helium, the ashes of the first cosmic furnaces. Lithium and beryllium, rare, almost accidental creations. Even now, after billions of years, the universe is still mostly hydrogen and helium, a reminder of that ancient time when the cosmos made its first attempt at chemistry. The universe becomes predictable. Up until this point, the universe had behaved like a storm, unpredictable, violent, random. But with the creation of the first nuclei, something changed. The universe became mathematical, predictable, structured, governed by laws that would remain unchanged for the next 13.8 billion years. The wild, chaotic energy of the beginning hardened into rules. Gravity curved space. The strong force knit quarks together. The weak force transformed particles. Electromagnetism waited patiently for the moment it could finally paint the universe with light. With these laws established, the universe was no longer improvising. It was following a script written in physics, and every particle obeyed. The growing stillness. As minutes turned to hours and hours to days, the universe's expansion continued steady, relentless, unstoppable. Every moment the cosmos stretched farther. Every stretch diluted the heat. Every dilution brought calm. The temperature dropped from 1 billion degrees to a few 100 million, then to tens of millions, then slowly to millions. Still unbearably hot but no longer hostile to the idea of structure. Protons and neutrons became loyal companions. Nuclei remained intact. Collisions, though fierce, were no longer immediately destructive. The universe was learning to breathe. Matter grows heavier than light. A profound shift occurred when the universe reached about 50,000 years of age. Until then, light ruled everything. Photons outnumbered matter by 1 billion to 1. Their energy dominated the behavior of the cosmos. But expansion stretched the photons' wavelengths, weakening their power. Light grew softer, gentler, less influential. Matter, on the other hand, kept its mass, its gravitational pull, its ability to gather, to sculpt, to shape. And so, slowly but surely, the balance of power shifted. This was the moment when the universe transitioned from radiation dominated, matter dominated. And that shift changed everything. Because radiation smooths the universe out, it fights structure, erases clumps, keeps everything evenly spread. But matter invites gravity to take control. And gravity loves clumps. Gravity loves structure. Gravity pulls matter together, gathering it, compressing it, shaping it into clouds and later into stars. With this shift, the universe took its first step toward forming galaxies. It was no longer just energy rushing outward. It was a place where matter could hold its ground, where gravity could win, where creation could become intentional. The fog still remains. Yet despite all this order, the universe was still shrouded in an impenetrable fog. Electrons zipped freely in every direction. Photons bounced endlessly, scattering, ricocheting, trapped. No light escaped, no clarity existed. The universe was still blind. This fog, this early plasma, was the final barrier, the last obstacle preventing the universe from revealing itself. But slowly, with every passing year, the fog thinned. Temperatures continued to drop. Collisions became less frequent. Electrons lost their frantic energy. The universe was ready for transparency. Not yet. But the countdown had begun. Everything that needed to exist was in place. The laws, the particles, the nuclei, the balance of matter and radiation. The universe had its ingredients, its rules, its direction. All that remained was the final transformation, the formation of atoms. When that happened, light after almost 400,000 years would finally be free. But that moment lies ahead. For now, the universe is preparing, cooling, waiting. The first particles are in place. The fog is thinning. Gravity is tightening its gentle grip. The universe is almost ready to reveal its first light. As the universe drifted through its first tens of thousands of years, something subtle but powerful unfolded beneath the fading heat. Something that would define the architecture of everything that would ever exist. Gravity, until now drowned out by the overwhelming pressure of radiation, finally began to speak with authority. At the beginning, photons ruled. Light pushed, light scattered. Light resisted anything that tried to come together. But with expansion stretching every wavelength, light grew weaker. It lost energy, lost pressure, lost its dominance, and as the universe transitioned into a matter-dominated era, gravity stepped forward like a quiet architect emerging from the shadows. For the first time, gravity had the power to shape reality. Not fully, not dramatically, not yet, but enough to plant the earliest seeds of the structures that would one day become galaxies, clusters, and cosmic webs. It began with small differences, tiny variations in density, minuscule ripples left behind by the early universe's quantum fluctuations, areas where matter was just slightly more crowded. Before this moment, those differences meant nothing. Radiation pressure smoothed everything out like a raging wind flattening hills of sand. But now the hills could stay. Now gravity could gather. Now matter could begin falling inward, collecting into the first invisible clouds. These clouds had no atoms yet, no stars, no heat, no light. They were made purely of bare nuclei, free electrons, and dark matter. And dark matter, mysterious, unseen, was crucial. Because while normal matter was still tangled in the hot plasma, dark matter was already free to move. It felt gravity. It responded. It gathered. While light remained trapped in the fog, dark matter began shaping the cosmic skeleton. Silent, invisible, but enormously influential. Dark matter builds the first scaffolding. Imagine a building being constructed in complete darkness. You cannot see the workers, you cannot see their tools, you cannot see the beams being placed, but you hear faint echoes, you sense movement, you feel the structure taking shape. That was dark matter in the early universe. We didn't know what dark matter is made of. We cannot touch it. We cannot see it. It does not interact with light, but it interacts with gravity, and gravity is enough. As the universe expanded and cooled, dark matter began forming enormous clouds, huge regions where its mass collected, drawing in more dark matter from the surrounding emptiness. These clouds are called dark matter halos. At first they were tiny, no bigger than dwarf galaxies. But as the universe grew, they merged, collided, deepened, and became gravitational wells. Invisible wells. Wells that normal matter would later fall into. You, your planet, your star, your galaxy, every atom that makes your existence possible, sits today inside one of these ancient dark matter halos that began forming during this era. The universe didn't know it yet, but it had just assembled the skeleton of cosmic structure. Baryons, the slower, heavier builders. Normal matter, called baryonic matter, was not as free as dark matter. It still lived inside the plasma, still collided constantly, still felt the resistance of trapped photons. It could not collapse quickly or form tight clusters. Every attempt at gathering was pushed back by light, but now the pushing was weaker, the pressure lower, the temperature cooler. And so, slowly, very slowly, baryons began sinking toward the deepening wells of dark matter. Not enough to form stars yet, not enough to ignite anything, but enough to drift, enough to accumulate, enough to follow the invisible pull of the dark matter skeleton. This slow drift laid the groundwork for everything that would later shine. For stars you need fuel, for galaxies you need mass, for light you need matter under pressure. And this drifting, this slow gathering was the beginning of the cosmic future. The universe's first sound waves. While dark matter ignored the glowing plasma, baryons were locked inside it, a mixture of protons, electrons, and photons, vibrating together like a cosmic drum. These vibrations, ripples travelling through the plasma, were the universe's first sound waves. Not sound in the way humans hear it, but real pressure waves moving through real material. Imagine the entire universe pulsing like a heartbeat, waves expanding, collapsing, rebounding. These waves created patterns, rings of higher and lower density, spreading outward through the plasma. Billions of years later, these ancient sound waves would leave imprints in the arrangement of galaxies we see today. The universe remembers everything, even its first vibrations. Approaching the moment of transparency. As the universe expanded through its first tens of thousands, then hundreds of thousands of years, temperatures continue to fall. 10,000 degrees, 8,000, 6,000, still fiery, still boiling, still too hot for atoms to exist, but close, so very close. Electrons were slowing down, protons and helium nuclei waited patiently. The fog, though thick, was losing its grip. The universe had already built its first particles, created the first nuclei split energy, from matter established the laws of physics, cooled by a factor of over 10,000, allowed gravity to take control, formed the skeleton of cosmic structure. Everything was ready. Everything was waiting. All that remained was for the universe to take one final step, the step that would change darkness into light. The formation of the first atoms, the collapsing of the fog, the freeing of photons, the birth of the first true light in the history of existence. That moment lies at the edge of Chapter 2, but not yet. At this stage, in these final centuries before recombination, the universe hovered between blindness and clarity, a world made of particles, but still without vision, a cosmos with the ingredients of light, but no pathway for it to shine. The anticipation was cosmic, the tension enormous, the transformation inevitable. Soon, the universe would open its eyes, but in this part of the story, it is still learning to build the pieces that will make sight possible. The universe, now hundreds of thousands of years old, was no longer the violent furnace of its birth. It was still hot, still dense, still glowing from within, but the once chaotic storm had quieted into a steady cosmic rhythm. Every moment brought more order, more structure, more calm. The fog of plasma still filled the universe from end to end, but the particles inside it had slowed just enough for something inevitable, something breathtaking to draw near. The creation of the first atoms. But before that moment could arrive, the universe had to pass through one last era of preparation, a time defined by balance, cooling, and an unexpected harmony between the forces of nature. The temperature where transformation becomes possible. At this stage, the universe had cooled to just a few thousand degrees. To us, that is still unbelievably hot enough to melt metal, vaporize rock, ignite anything we know. But to the early universe, this was the calm before dawn. This was the temperature where electrons, once racing chaotically at near light speeds, began slowing to a pace where they could finally be captured. Every degree of cooling mattered. Every moment of expansion mattered. Every centimetre of new space helped ease the frantic motion of particles. The universe was becoming gentle enough for structure to form, but not all at once. It was a gradual shift, a slow surrender of heat into the vastness of growing space. Protons were waiting. Helium nuclei were waiting. Electrons were wandering, searching for a place to belong. The universe was almost ready to assemble the first atoms, but a powerful barrier still stood in the way, a barrier made of light itself. Why atoms couldn't form earlier? Even though temperatures had dropped, there were still far too many photons, billions of them for every electron, and each photon carried enough energy to knock an electron off any nucleus before a stable atom could form. Imagine trying to glue pieces together in a hurricane. Even if the glue is strong, the storm tears everything apart. That was the early universe. Any attempt at forming an atom was smashed instantly by a passing photon. Electrons tried to bind, but they were kicked away. Protons reached out, but collisions overwhelmed them. The universe had the right pieces, but the environment was still too violent for those pieces to lock together. Something needed to happen. The universe has to cool more. Photons had to lose more energy. Collisions had to soften. And so, over thousands of years they did. The universe expanded. Temperature fell. Pressure dropped. And slowly the glow of the early plasma dimmed from brilliant white to deep orange to a warm red. The first dawn was approaching. Electrons begin to settle. Eventually the temperature fell to roughly 3000 Kelvin, a threshold of cosmic significance. At this temperature, photons no longer had enough energy to easily knock electrons away. The storm had weakened, the winds had quieted, the glue could finally hold. And for the first time since the universe was born, electrons began to settle into orbit around nuclei. Hydrogen atoms formed, helium atoms formed, a trace of lithium atoms as well. Each union was small, simple, tiny beyond imagination, but each was a victory over the chaos of creation. These were the first atoms in history, the first stable structures of matter, the first objects in the universe that could survive without being torn apart. With every electron captured, the fog grew thinner. Transparency crept across the cosmos like morning light spreading across an endless field. But then, just when the universe seemed ready to reveal itself, something strange happened. Recombination wasn't instant. You might imagine atoms forming suddenly, in a single sweeping moment where every electron locked into place. But the truth is more delicate. Recombination took time, thousands of years in fact. The process was messy. Electrons jumped in and out of orbits. Some were captured but quickly kicked away. Some drifted for ages before settling. Some wandered through space like lost travelers searching for a home. The universe was not a switch. It was a dimmer, and slowly, over countless years, the glow of the plasma faded as more and more electrons found their partners. Every union made the universe clearer. Every atom formed pushed back the fog. Every captured electron freed another photon to travel uninterrupted. Like dew evaporating from a field as the sun rises, like dust settling in a quiet room after a long night. The universe was becoming transparent. The moment, everything changed. Around 380,000 years after the Big Bang, a threshold was crossed. A tipping point, a transformation that had taken hundreds of thousands of years finally became complete. Enough atoms had formed, enough electrons had settled, enough collisions had stopped. The fog was gone, the plasma had become a gas, the photons were free. For the first time in cosmic history, light could move in a straight line without being stopped, blocked or scattered, and the universe, after so long in darkness, filled with a soft, warm glow. This glow wasn't from stars. They didn't exist yet. This glow wasn't from galaxies. They were still millions of years away. This glow was from the universe itself, the afterglow of creation, the first light ever born. We see this ancient light today as the cosmic microwave background, still travelling across the cosmos, still carrying the memory of the universe as first breath of clarity. Closing the chapter, with atoms formed, with light freed, with the fog dissolved, The universe was ready for its next phase. The Dark Ages were beginning, but this time the darkness was peaceful. A darkness where gravity could finally gather matter, where clouds could begin to collapse, where the ingredients of the first stars could drift into place. Chapter 2 ends with the universe quiet, clear, and ready. The pieces exist, the rules exist. The darkness has a purpose. The first light has been born, but the universe is waiting for the first stars to ignite. The universe had just undergone one of the greatest transformations in its history. For nearly 380,000 years, the cosmos existed as a glowing fog, a thick plasma where light and matter were trapped together, locked in a dance of constant collisions, but then suddenly quiet. The fog thinned, atoms formed, photons escaped. The universe became transparent. For the first time ever, light travelled freely through space, soft, warm, pale light, filling the cosmos with a gentle glow. No stars existed yet, no galaxies, only hydrogen, helium, and a faint whisper of lithium, the most basic elements, the simplest building blocks. And so began an era unlike any other, an era defined not by violence, not by chaos, but by silence. A long, still night. We call it the Cosmic Dark Ages. Not because the universe was empty of light, the first light was still travelling, but because nothing new shined. No stars burned, no planets reflected, no galaxies scattered light across the void. The universe was transparent, yes, but it had not yet learned to shine. And in this deep cosmic quiet, something remarkable began to unfold. The universe started to cool properly, deeply, steadily. The cooling of a newborn universe. Cooling had been happening since the very first instant. Every time space expanded, every time matter thinned, the temperature dropped. But this era was different. The sudden transparency changed everything. Before this moment, photons kept bouncing around inside the plasma, their energy trapped in a crowded storm of particles. But now they escaped. They moved outward, spreading across vast distances, stretching as the universe expanded. And as their wavelength stretched, their energy faded. Light became cooler, softer, longer. What was once a brilliant, fiery glow began drifting toward red, then to infrared, then to microwave. The first light dimmed not because it vanished, but because the universe was growing. Space itself stretched that light, like pulling a painted canvas wider and wider until the colours soften into a delicate, muted pattern. Even today, that ancient light continues to stretch, continues to cool, continues to whisper. Matter becomes calm. With electrons locked into atoms, collisions became gentler. The universe behaved more like a gas and less like a boiling soup. Hydrogen atoms floated freely, drifting through an expanding space that grew colder with every heartbeat. Temperatures plummeted from 3000 C to 2000 to 1000 to a few hundred. The universe cooled from a blistering furnace to something resembling the heat of a candle flame, still warm, still energetic, but no longer hostile to the possibility of structure. Hydrogen atoms began clumping together slightly, subtly pulled by the invisible hand of gravity. Not enough to form stars yet, not enough to ignite anything, but enough to drift, enough to gather, enough to begin the earliest motions that would one day form galaxies. Cooling was not just temperature dropping, it was pressure dropping, resistance dropping, chaos giving way to calm, and that calm allowed gravity to finally begin its slow, patient work. Gravity tightens its grip. Up to this point, gravity was present, but it struggled. Light pushed back, heat pushed back, density pushed back. But now the universe was cool enough that gravity's pull mattered. It didn't dominate yet that would come later, but it had influence. Inside the vast dark matter halos that formed during the earlier era, normal matter, hydrogen and helium began to fall inward. Not dramatically, not violently, but steadily, like dust settling after a storm. Each particle of matter felt the pull of a deeper well, a shadowy hand guiding it inward. These invisible dark matter halos were shaping the destiny of everything. Where they deepened, galaxy clusters would form. Where they thinned, voids would stretch across billions of light years. The map of the universe, the great cosmic web, was being traced in these moments by cooling matter drifting into unseen structures. The universe was dim, the universe was quiet, but it was preparing. Cooling wasn't at the end, cooling was the doorway. A perfect stillness. Imagine drifting through a vast space filled with atoms so spread out you could travel 1,000,000 kilometers without hitting a single one. Imagine no stars, no planets, no heat except the faint warmth left over from creation. Imagine a darkness so serene, so undisturbed that it feels almost sacred. That was the universe during this era. A perfect stillness stretching across unimaginable distances. Everywhere you looked, hydrogen floated silently, helium drifted softly. Dark matter shaped the landscape in ways no eye could see. Nothing flickered, nothing burned, nothing shone. It was a cosmic pause, a quiet breath between the chaos of birth and the brilliance of what was to come. Cooling was not inactivity. Cooling was preparation. Pressure decreased, temperature dropped, particles slowed, gravity grew stronger. Clouds began to form, huge clouds of hydrogen stretching across light years. These clouds, cooling further, would one day collapse under their own weight. And when they did, the universe would change forever. Because inside those cooling clouds lay the seeds of the first stars, the first sources of true light, the first objects capable of shining with heat, colour and structure. But the universe wasn't there yet. It still needed to cool further, still needed to gather more, still needed to drift deeper into this era of silence. Chapter 3 is the story of that cooling, the slow descent from heat to clarity, from plasma to gas, from blindness to possibility. And this part, this first phase, is the beginning of that long journey. The universe had become transparent. The first light had escaped. The fog had lifted. But this did not mean the cosmos was bright. In fact, the opposite was true. When light finally broke free and spread across space, it began a journey that would change. It forever a journey defined by stretching, fading, cooling. The first light started as a warm orange glow, soft even and comforting. But as the universe expanded, that glow dimmed, its wavelengths stretched by the fabric of space itself. A gentle orange became deep red. Deep red slipped into infrared. Infrared dissolved into microwave. And so the universe darkened. Not because light disappeared, but because it spread too thin for any eye, real or imaginary, to see it. This was the beginning of the longest night the cosmos would ever know. The night between transparency and the birth of the first stars. A night lasting millions of years. The universe without light. Even though photons now travelled freely, they did not illuminate anything. There were no stars to shine, no planets to reflect, no galaxies to glow. Hydrogen, helium atoms drifted silently through the cold, expanding void. Occasionally, atoms collided, but the universe was so empty. These collisions were rare, gentle, like snowflakes lightly brushing in a quiet breeze. Space had grown too vast for light to bounce off anything. Imagine a lantern glowing in the middle of a desert. Now stretch the desert to the size of the observable universe. Even the brightest flame becomes invisible. That was the universe now. It was transparent, yes, but empty of sources. A darkness filled not with chaos, but with potential. A darkness preparing for its first spark. Cooling becomes a cosmic sculptor. As the universe expanded, cooling brought balance. At 3000 degrees, hydrogen formed. At 1000 degrees, helium stabilized. At a few hundred degrees, the universe resembled a warm fog slowly dissolving into the cold. The cooling never stopped. Every second, space stretched. Every stretch thinned the energy of photons. Every thinning dimmed the glow. Cooling wasn't a passive effect, it was a force, shaping what matter could do. When temperatures dropped enough, new physics became possible. Structures could form, clouds of gas could thicken, gravity could begin compressing matter without heat instantly pushing back. Cooling was the silent architect. Like a master craftsman working in the dark, temperature carved the future of the cosmos with slow, patient strokes. Gravity quiet. Work. Gravity had always been present, but until now, radiation fought it fiercely. Any attempt by matter to clump was blown apart by the pressure of trapped light. But now the universe was transparent. The storm of photons that once smashed everything apart no longer interfered. And so gravity took its opportunity. It began gathering hydrogen atoms softly, invisibly, silently. In one region, a few atoms drifted closer. In another, the pull was slightly stronger. Nearby, a cloud began to form. These were not yet stars, not even close. These were the earliest gas clouds stretching across light years, almost too thin to notice. But gravity doesn't need thickness. It needs time. And now, for the first time since the universe was born, gravity had both space and time in overwhelming abundance. Over millions of years, these first clouds grew denser. They pulled more matter in. They thickened not dramatically, not quickly, but inevitably. Cooling allowed gravity to win. The universe was drifting into a deeper and deeper darkness, but beneath that darkness something was forming. Something incredible, something inevitable, something bright. The expansion that changes everything. As the cosmic cooling continued, the universe expanded into a state that would define all future structure. Space was not simply getting bigger, it was getting smoother. Fluctuations that began in the earliest moments, tiny differences in density, 1 part in 100,000 were now stretched across vast distances. These fluctuations became the maps of the future. Where matter was slightly denser, gravity pulled harder. Where matter was slightly sparser, gravity let go. Slowly, the universe sharpened its contrast. Dense regions grew denser, empty regions grew emptier. The cosmic web was emerging a vast network of filaments and voids that would one day host galaxies like pearls on invisible strings. Cooling made this possible. Without cooling, matter would race too fast, move too violently, remain too hot to settle. But now everything slowed. Gentle currents replaced violent flows. The universe became a calm sea, waiting for islands to rise. A darkness with purpose. It's easy to imagine darkness as emptiness, as nothingness, as the absence of everything. But this darkness was full of atoms, full of gravity, full of silent motion, full of faint cooling light, full of possibility. This was not the darkness of absence, this was the darkness of incubation, like the soil before a seed sprout, like the silence before music begins, like the breath before a word forms. The universe was not stagnant, It was preparing. Cooling was clearing the stage. Gravity was organizing the cast. Dark matter was shaping the set. Hydrogen was gathering as the script demanded. Something enormous was about to happen. Something the universe had never done before. A star was about to ignite. Not yet in this chapter, not yet in this moment, but soon. The cooling had set the conditions. The darkness had softened the universe. The atoms had formed, gravity had gathered, the universe was ready. The first star was waiting for its moment to spark. Cooling continued. Darkness deepened. The universe stretched wider and wider, its ancient glow fading into a whisper so soft that even if eyes had existed, they would have seen nothing but an endless silent void. But beneath that void, a slow, majestic tension was building. The hydrogen atoms drifting through the dark, each one unbelievably small, each one separated by colossal distances, were not floating aimlessly anymore. They were responding to gravity. Not the sharp, obvious gravity of planets or stars, those did not exist yet. This was the gravity of structure, of the cosmic web taking shape, of invisible dark matter guiding everything like a skeletal hand beneath the universe's skin. This stage, this quiet, heavy gathering, was the most important step before the birth of the first stars. It was in this era that the universe learned something new, how to collect itself. The first great clouds begin to form. Though space was unimaginably vast, gravity worked with infinite patience. Hydrogen atoms drifted, collided gently, then drifted again. Over millions of years, some regions collected a little more matter than others, just a tiny bit more. A few atoms here, a few atoms there. At first, these differences were small, barely noticeable even to the universe itself. But gravity loves imbalance. It feeds on it. Wherever matter was slightly denser, gravity pulled harder, and wherever gravity pulled harder, matter accumulated faster. This slow, self-reinforcing cycle created the very first true gas clouds. These primordial clouds were enormous, stretching across light years, made almost entirely of hydrogen with a touch of helium. They were thin, far too thin to resemble clouds on Earth, yet dense compared to the empty spaces around them. In these clouds, the future was beginning to gather. Hydrogen, the universe. Seth's first fuel, hydrogen, seems like the simplest thing in existence, a single proton holding a single electron. But this simplicity is deceptive. Hydrogen is the most important element in the universe, the key to stars, the key to light, the key to life itself. And now, cooling had made hydrogen stable, safe, abundant. Every hydrogen atom was a potential spark. Every cloud was a potential star. Every collection of atoms was the embryo of something bright, but none of it could ignite yet. Not until the clouds grew dense enough for gravity to crush them into blazing heat. That process had not begun. Not fully, not yet. But the universe was moving toward it with silent, unstoppable precision. Cooling causes collapse. Cooling wasn't just temperature dropping, it was pressure dropping. When the universe was hot, atoms moved too fast to gather. Heat pushed outward, fighting gravity at every turn. But cooling changed everything. Lower temperature meant slower movement. Slower movement meant less pressure. Less pressure meant gravity finally had room to act. Hydrogen clouds that once drifted lazily began to thicken, not by force, but by surrender. They surrendered to gravity as pulled away sand surrenders to a passing tide, slowly, softly, inevitably. Each cloud became a little heavier, a little denser. Its center became thicker, its edges more defined. These were the first pre-stellar clouds, the quiet wombs of future stars. the role of dark matter intensifies. While normal matter moved slowly, dark matter acted with purpose. Its halos deepened into enormous wells, pulling baryonic matter inward like falling snow toward the bottom of a deep valley. Dark matter didn't shine, didn't collide, didn't heat up. But precisely because of this, it could collapse faster and form structure sooner. Around these invisible halos, hydrogen clouds gathered thousands of light years across, setting the stage for the universe's first bright moment. Without dark matter, no galaxies would exist, no stars, no planets, no us. Every star you've ever seen, every galaxy photo ever taken, every sunrise in human history, all are shaped by the invisible skeleton formed in this era. The universe reaches its coldest point yet. As millions of years passed, the universe cooled to temperatures that would be chilly even on Earth. From a few thousand degrees, the cosmic background drifted down to just hundreds of degrees, then tens, then only a few. About 20 million years after the Big Bang, space had cooled to nearly the temperature of a warm summer day on Earth. By 50 million years, temperatures dropped below freezing. But unlike Earth, this cooling was not dangerous, it was necessary. Only a cold universe could allow clouds to collapse deeply enough to ignite heat at their centers. Only a cold universe could enable star formation. Only a cold universe could awaken the next phase of cosmic evolution. Cooling was the permission gravity had been waiting for. The quiet tension before ignition. The primordial hydrogen clouds reached a dramatic moment, a point of no return. Some clouds grew so massive that gravity began to overpower their internal pressure. Their centers thickened, density rose, temperatures inside began to climb, slowly, very slowly, but undeniably. This rise in heat was the first stir of future fire. The clouds had not ignited, yet they were still cold compared to stars, but deep inside, the earlier sparks of compression were beginning to glow. Tensions grew inside these clouds like the quiet breath a candle takes before it bursts into flame. If someone could float inside one of these clouds suspended in silence, weightless in darkness, they would feel it, a gathering, a tightening, a pressure shifting inward, constricting gently, preparing for something colossal. The universe was holding its breath, stars were coming, and with them, the universe would awaken from its long, silent night. The universe had grown cold, not the biting cold of winter, not the temporary chill of a passing night, but a deep, ancient cold, the kind that settles across billions of kilometers and touches everything with perfect stillness. This cold was not an enemy. It was a sculptor. It slowed atoms, softened their collisions, allowed gravity to gather and compress them with tender but relentless arms. Millions of years had passed since the first light escaped the fog, since the universe became transparent, since photons began their eternal journey. Now, the stage was set for the next great transformation, one that would end the cosmic night and flood the universe with radiant brilliance. But before the first star could ignite, the universe had to pass through one final era of silent preparation. The growing weight of the hydrogen clouds. The hydrogen clouds that gravity was pulling together had grown vast, stretching across dozens, sometimes hundreds of light years. Each cloud contained unimaginable amounts of gas, yet remained unbelievably thin compared to air on Earth. If you stood inside one, if such standing were possible, you wouldn't feel air, pressure, or wind. You would feel nothing. The atoms were spread so far apart you could travel for days without encountering a single one. And yet these clouds were dense enough compared to the emptiness around them That gravity finally took notice. Slowly, like a whisper turning into a hum, gravity intensified its pull. The clouds began to collapse inward, not all at once, not violently, but gradually, as if the universe itself were gently guiding them toward the destiny. Gravity, a secret work, building heat. As the hydrogen clouds collapsed, their centers grew denser, and as particles crowded closer together, they bumped, pressed, rubbed against one another. These collisions produced heat, very faint at first, so faint that the surrounding cold absorbed it immediately. But with every passing century, with every contraction of the cloud, the central temperature rose. Gravity was no longer just gathering matter. It was beginning to ignite motion, to squeeze hydrogen atoms into a space too tight for comfort. Compression created heat. Heat created motion. Motion resisted gravity. Gravity squeezed harder. This feedback loop was the recipe for something spectacular, the birth of a star. But the universe had not reached that point yet. Now came the most delicate phase. The core forms a star, its first heartbeat. Deep inside the collapsing cloud, a core was forming. Not a star, not yet, but a protostar, a warm, dense knot of hydrogen gathering in the darkness. Temperatures inside this core climbed to thousands of degrees, still far below the millions needed for fusion, but enough to glow dimly with the softest infrared light. No human eye could have seen this faint glow. No creature could approach this cosmic embryo. But the glow was real, a first heartbeat in a cloud waiting for fire. As temperatures climbed, the outer layers fell inward more rapidly, feeding the growing core. Every moment gravity tightened its grip. Every moment heat increased. The universe had been cold for millions of years, but inside these cores, warmth was returning. A warmth entirely new, never before seen in cosmic history. The cores grew brighter, not visible light, but the first hints of thermal emission. It was as if the universe were lighting the faintest sparks under a blanket of darkness. The cold universe nears its first flame. This was the final stage of cooling, the moment before ignition. Temperatures outside the cores were near absolute zero. Hydrogen gas drifted like quiet mist toward the gravitational center. Inside the cores, temperatures were rising rapidly, 10,000 degrees, 50,000, 100,000. Still not enough. Hydrogen fuses only at millions of degrees, but the direction was clear, the momentum unstoppable. The universe, once overwhelmingly hot, was learning to create heat in small, focused places. Heat controlled by gravity. Heat organized by pressure. Heat that could override the cold. This was the most delicate balance in nature and the key to everything. Gravity trying to ignite the first fire without letting the cloud collapse too fast. If gravity squeezed too aggressively, the cloud would tear apart. If gravity squeezed too softly, the cloud would never heat enough to shine. But the universe had patience. It had time. More time than any future star would ever experience again. Over tens of millions of years, the cores grew tighter, denser, hotter. The hydrogen atoms rattled furiously, trapped in a cage of gravity's making. The cold universe was on the verge of creating the first source of light since the beginning of time. The moment before ignition. Everything was ready. The first gas clouds were collapsing. The earliest protostars were warming. Gravity had gathered the fuel. Cooling had allowed matter to settle. Dark matter halos held the clouds together. Hydrogen nuclei were bumping hard enough to begin the earliest whispers of what would one day be nuclear fusion. The universe stood at the threshold of its second dawn, a dawn far brighter than the soft first light of recombination. A dawn powered not by cooling, but by fire. The first stars were moments, cosmically speaking, from igniting. And once they did, the universe would never be the same. The darkness would end. The night would glow. The cosmos would awaken with brilliance and heat for the very first time. The cooling era was complete. The universe had prepared the stage. Chapter 3 ends at the edge of ignition, the breath before flame. In Chapter 4, the first stars will ignite and paint the universe with light. The universe had been silent for millions of years. Silent not in sound, for sound could not travel the emptiness, but silent in light. A vast cosmic night stretched across every direction. Not the warm, familiar night of Earth, pierced by stars and planets, but a night so total that there were no shapes, no outlines, no glimmers, no direction at all. A night without stars. A night that had lasted since the moment the first light escaped the fog hundreds of thousands of years earlier. During this long cosmic night, hydrogen clouds, colossal in size, delicate in texture, drifted through the darkness like ghosts. Gravity pulled them inward, cooling slowed them, and pressure built quietly inside them. Deep in their centres, protostars formed warm knots of hydrogen, heating slowly under the weight of billions of tons of gas. And now, after millions of years of silent collapse, the cores of the densest clouds were approaching a threshold no atom had ever crossed before. A temperature so high that hydrogen so gentle, so simple, would be forced to fuse. And in that moment, the universe would ignite, not just with heat, but with light. Light bright enough to shatter the darkness that had wrapped the cosmos since its birth. We stand now at the edge of that moment, the moment when the universe opens its eyes for the second time, the rise of the first protostars. The earliest protostars were nothing like the stars we know. They were massive, hundreds of times the mass of our sun, sometimes thousands. They did not shine, not yet. They were still dark embryos, warming from within, waiting for the moment gravity's pressure would become so intense that atoms could no longer resist. As hydrogen atoms compressed into tighter and tighter spaces, the temperature in the core climbed relentlessly. 100,000 degrees, 200,000, 500,000, still not enough. Gravity continued its slow squeeze for millions of patient years. One day, cosmically speaking, the core reached 1 million degrees. At this temperature, the protostar began glowing in infrared, a warmth still invisible to any eye, but a hint of what was coming. Then, when the temperature approached 10 million degrees, something extraordinary happened. Hydrogen nuclei, simple protons, began moving with so much energy that when they collided, they stuck together. They fused. The most important reaction in the universe had just begun. Nuclear fusion, the universe's first fire. When two hydrogen nuclei fuse, they form helium and release energy. Not just a spark, not just heat. An explosion of light created at the centre of a collapsing cloud. This energy pushed outward. Gravity pulled inward. A balance formed, a perfect tension between collapse and explosion. That balance is the definition of a star. And so, in that moment, the first star in the universe ignited. It did not flicker like a candle. It roared to life. The first generation of stars, called Population 3 stars, were enormous. Many were hundreds to 1,000 times larger than our sun. They burned hotter, brighter, faster than any stars that came after. When these stars ignited, they flooded the surrounding dark with ultraviolet light so intense it tore electrons away from nearby atoms. The universe, dark for millions of years, suddenly had points of blazing brilliance, points so bright they pierced billions of kilometers with raw, searing radiation. They were not gentle stars, they were cosmic torches, and they began rewriting the universe. The end of the cosmic dark ages. The moment the first stars ignited, the cosmic dark ages began to lift. Each new star acted like a lantern in the middle of a vast cosmic desert, a desert that had known no light since its earliest days. These first stars illuminated their surroundings with blue-white fire, their heat impossible to imagine. They were short-lived, furiously burning through their hydrogen in only a few million years, a blink compared to our sun's 10 billion year lifespan. But in their short lives, they changed everything. Their light began to carve pathways through the darkness. Their heat ionized the cold hydrogen around them. Their gravity sculpted the gas into spinning disks. Their winds blasted matter away and carved the first cavities in the primordial clouds. A universe once calm and cold was now alive with motion, heat, and luminosity. The ancient night was ending. The first stars were titans. Population of 3. Stars were not ordinary stars. They were giants, behemoths, cosmic monsters of heat and mass. Their surfaces burned at nearly 100,000 degrees, far hotter than most stars in the modern universe. Their light was so intense it could strip electrons from atoms tens of thousands of kilometers away. Their interiors forged new elements, carbon, oxygen, silicon, the ingredients of planets, life, and everything familiar. They were the universe's first factories, and though they lived briefly, their deaths were spectacular. When they ran out of hydrogen, they collapsed rapidly into cores of dense helium. Temperatures soared further hundreds of millions of degrees, fusing heavier elements until iron formed. And then, with nothing left to burn, they exploded in supernovae so powerful, they shook the surrounding space. These explosions expelled heavy elements across the universe, seeding the next generation of stars with the ingredients for complexity. Without the first stars, no second generation would exist. No planets, no carbon, no oxygen, no life. These ancient titans were the grandparents of everything alive today. The universe begins to glow. As more and more stars formed, the darkness receded further. Clusters of stars lit up early halos. Star-forming regions burst with ultraviolet light. The gas between stars began to warm and become partially ionized again. The universe was no longer quiet. It was no longer cold. It was no longer empty. It was now a place of fire, light, motion, soundless explosions, and the birth cries of countless stars. The second dawn had arrived. The long night was ending, and the universe, once defined by silence, was beginning to sing. The first stars had ignited, not quietly, not gently, but with a brilliance so fierce that the universe dark for millions of years felt, for the first time, the touch of true starlight. These were not stars like the ones we see today. They were the universe's first attempt, the raw, unrefined prototypes of everything that would come after. Massive, violent, unstable, magnificent. Their ignition marked a turning point, a transformation so profound that the entire cosmos shifted in response. The darkness that had defined the universe since recombination was no longer absolute. Shadows broke, regions glowed, and the cold hydrogen mists that had once floated silently now shimmered with ultraviolet radiation. The universe was waking up from its long, still night. The first stellar nurseries. The earliest stars did not form alone. While the universe was vast beyond imagination, gravity worked region by region. pulling matter into pockets that became the first stellar nurseries. These nurseries were nothing like modern star-forming regions visible in telescopes today. They were quieter, simpler, and made almost entirely of hydrogen and helium. But they were huge. Some clouds contained enough gas to form hundreds or thousands of massive stars, each one dozens to hundreds of times the size of our Sun. These were cosmic cradles, primordial regions where gravity concentrated gas until it glowed with the fire of fusion. Inside these deep pockets, protostars grew rapidly far faster than modern stars form. Why? Because the early universe was pure. There were no heavy elements to slow cooling or disrupt collapse. Hydrogen gas fell inward easily, without metals or dust to scatter infrared radiation. The first stars formed fast, large, and hot. Gravity didn't hesitate. Hydrogen didn't resist. And so, like sparks igniting dry tinder, clusters of massive stars erupted across the earliest cosmic halos, the light that began to break the dark. When the earliest massive stars came to life, their ultraviolet radiation cut through the surrounding gas like a cosmic blade. This radiation ionized hydrogen, stripping electrons away and turning neutral atoms back into plasma. But unlike the early universe's opaque plasma, this new plasma was thin, spread out, and transparent. The stars carved out enormous bubbles, ionized regions that expanded outward in all directions. Imagine each star as a miniature sun, creating a growing bubble of blue-white fire in every direction. These expanding spheres of ionization began the next great transformation of the universe, rionization, an era when the entire cosmos would be reheated, recharged, and reshaped by the fierce radiation of the first stars. This was not a swift process. Rionization took hundreds of millions of years, but this was its beginning. The first sparks, the first fires, the first light strong enough to fight the ancient dark. The short lives of the first giants. For all their glory, the first generation of stars, Population 3 lived brief, violent lives. Their mass was their curse. A star's lifespan depends on how fast it burns fuel, and the most massive stars burn hydrogen with terrifying urgency. A star like our Sun burns calmly for over 10 billion years, but the earliest giants, 100 to 1,000 times more massive, burn through their fuel in only 2-3 million years. Their light was fierce, their heat cosmic, their gravity immense, but their lives were short flashes in the long story of the universe. Yet, in those few million years, they achieved what the universe had been waiting for. They forged the first heavy elements. They seeded the cosmos with carbon, oxygen, nitrogen, the ingredients of life. They exploded in supernovae that scattered metals across space for the first time. They were the universe's first alchemists. Their deaths were as important as their births. The first supernovae shake the cosmos. When the first massive stars died, they did not fade. They erupted. The explosion of a Population 3 star was unlike any modern supernova. These deaths were far more energetic, more like cosmic detonations that ripped through newborn galaxies with unimaginable force. Shockwaves blasted through surrounding gas clouds, compressing some regions and dispersing others. Some collapsing clouds were torn apart before they could form new stars. Others were compressed so tightly that they ignited second-generation stars much sooner than they otherwise would have. These shockwaves carved the universe's early landscape, shaping star formation for millions of years. Supernovae also produced heavy elements iron, silicon, carbon, and flung them across space. For the first time, the universe had metals. With metals, star formation would change forever. Cooling became more efficient. Clouds could collapse in new ways. Stars could form smaller, more stable, more long-lived. In other words, the first stars made the next stars possible. They were the architects of the modern universe. The second generation begins. Once the early supernovae passed, the gas they enriched began to gather again. This time, though, the clouds behaved differently. Metals allowed gas to radiate heat more efficiently, cooling down faster and collapsing into tighter shapes. This led to stars much more similar to stars we know today. Smaller, longer-lived, less violent, more stable. These second-generation stars, population 2, would fill the early galaxies with warm yellow and white light, lasting for billions of years. Some of these stars still exist today. When we look into the Milky Way's oldest clusters, we are seeing stars born from the ashes of the first giants. The universe was transitioning from chaos to stability, from darkness to structure, from isolated sparks to vast regions of starlight. The cosmic night was ending. A universe lit by stars was beginning. The first stars had burst into existence like cosmic firestorms, brilliant, brief, and unstoppable. Their ultraviolet light carved pathways through the darkness. Their supernovae seeded the universe with new elements. Their gravity shaped the clouds around them. Their heat reawakened the cosmos from its long, silent night. But a star, no matter how massive, cannot define the structure of the universe alone. One star is light. A group of stars is brilliance. But a galaxy is architecture. It is the universe's first great city, its first organized structure, its first attempt at beauty on a colossal scale. This part of our journey explores how the earliest stars the giants forged in deep darkness began to gather, cluster, collide, and shape themselves into the first galaxies. Galaxies did not exist at the moment the first stars ignited. They came shortly after, but in cosmic terms, shortly means tens or hundreds of millions of years. Still, compared to the lifespan of the universe, galaxies formed quickly, as if gravity had been waiting for the darkness to clear so it could begin sculpting the cosmic landscape. Gravity's masterpiece begins. Gravity, until now working quietly in the background, finally stepped into the spotlight. It had been preparing for this moment since the earlier seconds of the universe, shaping dark matter halos, deepening invisible wells, guiding hydrogen gas into clusters. Now, with stars blazing at their centres, those halos lit up like lanterns in a boundless night. Each halo became a cosmic oasis where gas, stars, dust, and dark matter swirled together in spiralling harmony. The first galaxies were not organised spirals like the Milky Way. They were chaotic, irregular clusters, lumpy, asymmetric, more like cosmic clouds than refined cities. But they were galaxies all the same, and they were magnificent. The first galaxies were small but fierce. The earliest galaxies were tiny compared to the majestic galaxies we see today. Many were only a few thousand light years across, mere sparks next to the giants that would come later. But what they lacked in size, they made up for in intensity. They were dense, packed, overflowing with star formation. Their cores blazed with massive population 3 stars. Their outskirts swirled with collapsing hydrogen clouds. Their gravitational centres pulled everything inward like whirlpools in the vast ocean of space. These galaxies pulsed with raw creation, more like cosmic furnaces than the orderly star cities we are familiar with today. Every massive star that ignited or exploded inside them reshaped their structure. Every supernova blew holes through their gas clouds, carving caverns of emptiness surrounded by sharp ridges of heated matter. In these clouds, new stars formed smaller, longer-lived, more stable. Galaxies were becoming star factories. The universe was learning to recycle, to refine, to improve. The era of galactic mergers. The early universe was small compared to its size today. Distances between galaxies were shorter, velocities were faster, collisions were frequent. Galaxies collided often, sometimes gently, sometimes violently. When two early galaxies collided, stars rarely hit each other. Space is too vast for that. But their gas clouds smashed together, triggering enormous waves of star formation. New stars ignited by the thousands. Massive clusters formed in bright bursts. Shockwaves raced through the merging halos, mixing their material into something new. These mergers were not destructive, they were creative. They built bigger galaxies from the fragments of smaller ones. The Milky Way, our own home galaxy, is the descendant of countless ancient mergers, a cosmic tapestry woven from galaxies that lived and died billions of years before Earth existed. In the early universe, mergers were constant, and each one reshaped the architecture of the cosmos. Black holes, born in the hearts of titans. The massive stars of the early universe burned hot and fast. Many ended as supernovae, but others, the heaviest among them, collapsed directly into black holes. These black holes, formed in the hearts of population 3 stars, were the first of their kind. Some were the mass of a few suns, others reached dozens. A rare few may have become hundreds. Alone, they were simple, silent, invisible. But galaxies are full of stars, and stars are full of gravity. And gravity draws everything together. Soon, black holes formed at the centers of collapsing galaxies. Every time two galaxies merged, their black holes sank toward the center and spiraled around each other like dancers locked in infinite embrace. Eventually they collided. These black hole mergers created larger and larger black holes. Over hundreds of millions of years, these central black holes became the seeds of supermassive black holes, the giants that would one day anchor galaxies like the Milky Way and Andromeda. Even in the earliest age, the seeds of the future were already growing quietly, invisibly, powerfully, the first signs of structure. By the time the universe reached 200 to 300 million years of age, the cosmic landscape had changed beyond recognition. What once was a cold, dark void was now a complex tapestry of glowing galaxies, swirling gas, and expanding bubbles of ionized hydrogen. The darkness had broken. The second dawn was complete. Clusters of galaxies began forming along filaments of dark matter, like beads threaded on cosmic strings. Voids expanded between them, vast empty regions, nearly devoid of matter. The cosmic web, born from tiny fluctuations in the early plasma, was now visible in light for the first time. The universe had structure, texture, organization. It was no longer a smooth expanse of cooling hydrogen. It was a young, vibrant cosmos filled with stars and galaxies. The age of fire had begun. The universe was no longer a silent ocean of darkness. Not after the first stars were born, not after their ultraviolet fire spread across space, not after their supernovae tore open the fabric of early galaxies and scattered the first metals into the void. The long night that had stretched for millions of years was ending. Slowly, beautifully, inevitably. This final part of Chapter 4 tells the story of how those first stars, brief as lightning, but brilliant beyond measure, changed the universe forever. They did not simply glow, they rewrote the cosmos, the light that cut through everything. When the first stars ignited, they unleashed torrents of ultraviolet radiation light so energetic It could tear electrons from atoms, break hydrogen apart, and push back the darkness with a force creation had never seen. This light didn't just illuminate space, it changed it. It ionized the cold hydrogen that filled the early universe, transforming the neutral atoms formed during recombination back into charged plasma. But this new plasma was different thin, spread out, transparent. The universe did not become foggy again. Instead, it became carved into bubbles, vast regions around each new star where hydrogen was stripped of its electrons and pushed outward like waves from a rising tide. The early universe resembled a cosmic foam, millions of glowing bubbles expanding from every star cluster like lanterns floating in endless night. These bubbles grew, merged, overlapped, until eventually they filled all of space. This was the epoch of ionization, one of the most dramatic transformations in cosmic history. It marked the true end of the ancient darkness. The universe gains transparency. Forever after ionization, the universe became permanently transparent. Never again would light be trapped in the dense fog of early plasma. Never again would photons struggle to travel more than a hair's width before colliding with an electron. Now, light could travel trillions of kilometers without interruption. It could cross galaxies. It could bridge the voids between them. It could reveal the cosmic web in all its elegance and scale. Even today, 13.8 billion years later, we see the universe clearly because the first stars made it possible. Their ultraviolet fire burned away the last remnants of the early fog. Their heat freed electrons from hydrogen and made space clean and transparent. Every telescope image, every glimpse of distant galaxies, every piece of cosmic light that reaches your eyes exists because the first stars cleared the way. The birth of cosmic metals. The first stars were pure hydrogen and helium, the only elements the universe had created during its turbulent beginning. But stars are alchemists. Inside their cores, the unimaginable pressure fused hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into heavier and heavier elements right up to iron. And when the most massive among them exploded as supernovae, they hurled these newly forged metals into the surrounding space. These metals, carbon, nitrogen, oxygen, silicon, would become the foundations of everything complex: planets, atmospheres, water, life, you, every heavy atom in your body, every atom of calcium in your bones, every iron atom in your blood, every carbon atom in your cells was forged in the belly of a massive star that died billions of years before Earth existed. The early universe was simple, monotone, uniform. The first stars added variety, complexity, colour. They seeded the cosmos with the ingredients for everything that would follow. The making of the galactic web. As the first galaxies grew fueled by star formation, shaped by dark matter, brightened by the brilliance of stellar giants, they began assembling themselves along the invisible highways created by gravity. These highways were the dark matter filaments, vast threads of invisible mass stretching across the universe like an enormous three-dimensional spider web. Galaxies collected along these filaments, clustered around intersections, and avoided the cosmic voids where little matter existed. By 500 million years after the Big Bang, the universe had taken on a structure that still exists today. Filaments of galaxies bordering immense empty voids, the cosmic web. A map of structure woven from gravity, time, and the ashes of ancient stars. The first stars lit these filaments. The first galaxies strengthened them. The first supernovae enriched them. everything was falling into place. The universe becomes a place of fire and shadow. With stars igniting everywhere, the darkness did not disappear, it evolved. Now the dark was no longer empty. It was filled with silhouettes, the shapes of early galaxies, clusters, dust clouds, star-forming regions. Light illuminated some areas, leaving others in contrast, creating shadow, depth, structure. The universe had gained dimension. It was no longer a uniform glow or an empty dark. It was a canvas painted with fire. And yet, in this cosmic dawn, the universe was still young, only a few 100 million years old. Its greatest structures were still in infancy. Its future marvels awaited billions of years of evolution. But the spark had been lit. The path had been revealed. The night had been broken. The cosmos was awake. Ending Chapter 4. A universe filled with light. The ignition of the first stars was not merely an event. It was the turning point when the universe stopped cooling and began shining. It was the moment when structure ignited, when galaxies began to grow, when light carved pathways through ancient hydrogen, when the first heavy elements were born in stellar cores. From this moment onward, the universe was no longer defined by what it lacked, but by what it could create. The dark past was over. The bright future had begun. The universe was no longer a silent void. Not after the birth of the first stars, not after their light-carved great glowing bubbles through the hydrogen fog. Not after early galaxies began to cluster along the dark matter filaments, like jewels on invisible threads. Starlight had returned, heat had returned, fire had returned. But something else had appeared as well, something quiet, enormous, and often forgotten. Darkness. Not the old, uniform darkness of a universe before stars existed, but a new kind of darkness. The darkness between stars. A darkness woven with light. A darkness shaped by gravity. A darkness full of structure but empty of matter. A darkness so vast that even the newborn galaxies could not hope to fill it. This darkness was not empty. It was the stage on which the next chapters of cosmic history would unfold, and it was growing. A universe getting brighter and darker. When the first stars ignited, their brilliant light pierced the void, illuminating everything around them. Yet paradoxically, their arrival also revealed something profound. Most of the universe was still dark, and would remain dark forever. As galaxies formed and gathered together, they concentrated matter into bright islands, clusters of stars glowing like embers in the night. But around every galaxy, there stretched unimaginable distances of cold emptiness, huge expanses where no stars existed, no heat flickered, no light had ever touched. These were the early interstellar and intergalactic voids, vast seas of near nothingness that made the bright newborn galaxies look tiny by comparison. Even today, billions of years later, the universe is 9999 empty space. The first stars lit the cosmos, but they also revealed how deep and endless its shadows truly were. Gravity forms islands in an endless ocean. To understand the darkness between stars, we must understand how galaxies formed. Gravity gathered matter not evenly but in lumps. These lumps, shaped by primordial fluctuations, became the earliest galaxies, but gravity didn't gather matter everywhere. Between the clumps, matter was scarce. The cosmic web had empty spaces, regions where gravity was weak, where matter drifted outward, never settling into place. These empty regions were the first voids, and as the universe expanded, these voids expanded faster than the bright regions. Imagine dew forming on a spider web. The droplets collect along the threads, but everything in between stays dry. The universe behaved the same way. Stars gathered where dark matter formed deep wells. Galaxies grew in those wells, but nothing collected in the gaps. Every time new stars formed, every time galaxies merged, every time clusters grew, the dark spaces between them grew even larger. The universe was becoming structured but also increasingly empty. Recoiling from explosion after explosion. The first supernovae were ferocious beyond imagination. When the earliest massive stars died, they destroyed everything around them, shattering gas clouds, pushing matter outward, heating the surrounding voids to temperatures higher than stellar surfaces. These explosions pushed material away from galaxies, widening the empty regions between them. In some pockets of the cosmos, supernova blasts were so frequent that galaxies could not form nearby. The violence of light created larger, colder, deeper seas of dark. These voids, once small and subtle, swelled into enormous cavities, hundreds of thousands of light years across. Space was becoming a patchwork of brilliant clusters surrounded by expanding hollows. The more the universe lit up, the more it revealed its vast invisible emptiness. The first black holes carve shadows. The early universe had another architect of darkness. Black holes. Massive stars collapsed into black holes, often at the centres of early galaxies. Some merged, some consumed, some spun so fast they dragged space around them like whirlpools. Black holes did not illuminate, they hid. Their presence warped the surrounding regions, creating gravitational shadow zones where light bent, curved, or vanished entirely. The more galaxies formed, the more black holes grew, and the more black holes grew, the deeper the shadows between stars became. The darkness of the early universe was no longer smooth. It had texture, depth, shape. It became a darkness full of secrets, silent but structured, empty but powerful, invisible but real. Cold hydrogen fills the voids. Even in the emptiest regions, the universe was not truly empty. Hydrogen, the most abundant element, filled nearly every corner of space. But in the voids, the hydrogen was so thin that it behaved like a faint ghost too spread out to gather, too cold to ignite, too isolated to join galaxies. This diffuse hydrogen absorbed light faintly, leaving tiny fingerprints on the earliest cosmic signals. Astronomers today can still see these shadows called the Lyman Alpha Forest, revealing the cold, silent strands of hydrogen in the most ancient darkness. These shadows, these faint traces, are the last whispers of the early cosmic voids. The darkness was not empty, it was waiting. This new era after the first stars but before galaxies fully matured was a time of contrast. Brilliant clusters of light surrounded by oceans of silence. Stars forming in fierce bursts while the universe around them remained calm, quiet, untouched. The darkness between stars filled with potential. Potential for galaxies to grow. Potential for matter to collapse. Potential for cosmic structures to become vast and intricate. The universe was no longer a featureless void. It had lights, it had shadows, it had structure, it had purpose. And this purpose would soon give rise to the next great transformation. The creation of the first galaxies powerful enough to reshape the universe. But before that could happen, the darkness had one more role to play, a role you will feel more deeply in the next part. The early universe had begun to glow. Points of starlight rising inside the first galaxies, supernovae exploding like cosmic thunder, heavy elements drifting into space for the first time in history. Yet for every island of radiance, there stretched an ocean of pure emptiness, silent, cold, and overwhelmingly vast. This contrast defined the young cosmos, brilliant pockets of creation surrounded by deep abysses of unlit space. The more stars appeared, the more profound the darkness between them became. Not because darkness was winning, but because light had revealed just how enormous the universe already was. The stars were few, the universe was immeasurably large, and the space between lights grew faster than the lights could multiply. Light travels, but it cannot fill infinity. When the first stars ignited, their light radiated outward at 300,000 km/s, the fastest speed allowed in nature. But the universe itself was expanding even faster. Space stretched like an inflating ocean, pulling galaxies apart, carrying stars away from one another so quickly that even light could not bridge the growing divide. Imagine lighting a candle in a room that expands faster than the candle's glow can reach the walls. No matter how bright the flame burns, its light can never touch the edge. That is the universe. The first stars shined fiercely, but their brilliance was swallowed by the accelerating void. Light travelled far, but the darkness travelled farther. And this made the emptiness between stars and galaxies larger than any distance the human mind could ever picture. The gravity of loneliness. Gravity drew stars together into clusters, small communities of light born from ancient hydrogen clouds. But between these clusters stretched regions so vast, so empty, that even after billions of years, some have never seen a single photon from the nearest galaxy. These voids were places where gravity lost the tug-of-war against expansion. Matter could not gather there. Stars could not form there. Galaxies could not survive there. Yet these voids weren't failures or forgotten corners of space. They were the natural shape of a universe sculpted by early fluctuations. Where matter was slightly denser, light would one day shine. Where matter was slightly thinner, darkness would reign forever. This unevenness, imprinted in the very first second of cosmic history, gave rise to everything: galaxies, stars, planets, voids, light and darkness woven together by chaos and gravity. Silence, larger than galaxies. Inside these voids, the darkness was not frightening. It was peaceful. There was no sound, no motion, no swirling storms of matter. Just the gentle drift of hydrogen atoms so far apart that each one felt like a lonely traveller crossing a desert with no horizon. If a single hydrogen atom in a void had consciousness, it would never encounter another in its entire lifetime. This is not an exaggeration. The vastness of these voids is so extreme that the nearest atom could be kilometers away. A vacuum so perfect that even the cleanest lab chamber on Earth is a roaring storm by comparison. This is the true nature of the space between stars, a desert where nothing touches anything. The first galaxies navigate a fractured universe. Even the earliest galaxies, small and irregular as they were, felt the pull of isolation. Some formed near dense filaments of dark matter, future locations of galaxy clusters and superclusters. Others formed on the outskirts, near the edges of voids, with little gas to feed new stars and almost no neighbouring galaxies to merge with. These galaxies lived quiet lives, dim, lonely, waiting for billions of years before joining larger galactic families. Some of the faintest galaxies today, ancient dwarfs orbiting the Milky Way, are living fossils from this era of isolation. They are the survivors of a universe where distance itself was the greatest barrier. Light reveals the immensity of dark. The first stars created an unexpected effect. By illuminating small regions, they made the empty regions look even darker. This contrast light against nothing gave the universe its first sense of scale. Suddenly the cosmos wasn't a uniform fog, it was structured. Some places were bright and busy, others quiet and infinite. The existence of light taught the universe how big it truly was. Darkness, once all there was, no longer felt like nothingness. It became a canvas, a background that made starlight meaningful. Darkness was not the enemy. It was the frame around every cosmic masterpiece. Cold shadows where future galaxies will grow. Inside the voids, nothing happened quickly, but even emptiness was evolving. Gravity from distant galaxies tugged faint hydrogen toward them, creating currents of matter drifting slowly, sometimes taking 1 billion years just to move a fraction of a light year. Over time, these gentle flows would feed new galaxy formation on the cosmic filaments. The darkness was not static, it was waiting, preparing, holding potential. Some galaxies that shine today were once particles drifting silently in these frozen voids. The universe realizes its shape. By now, hundreds of millions of years after the first stars, the universe had settled into a clear pattern. Islands of light floating in oceans of darkness, galaxies along filaments, stars inside galaxies, black holes forming their seeds, voids stretching across billions of kilometers. The cosmic web, born from tiny fluctuations in the earliest plasma, was now illuminated by starlight for the first time. The darkness had structure, it had scale, it had meaning, and in that meaning lay the next phase of cosmic history, the rise of fully formed galaxies, the birth of supermassive black holes, and the growth of cosmic complexity. But that story belongs to the next part of our journey. The universe had begun to reveal its architecture, not through maps or boundaries, but through a delicate balanced light forming in the densest places, darkness stretching endlessly everywhere else. Light illuminated the threads, darkness revealed the gaps. Together, they created the first true picture of the cosmos. This part of our journey explores how that structure grew, how the darkness between stars shaped the light, and how the light sharpened the shadows. The cosmic web was emerging, but it was not a flat grid, nor a simple lattice. It was alive with motion, a dynamic system sculpted by gravity, expansion, and the memory of the universe's earliest moments. To understand the universe, we must understand this web. To understand the web, we must understand the shadows. And to understand the shadows, we must understand the emptiness between every spark of light. The cosmic web takes shape. The earliest galaxies formed not in random positions, but along deep valleys of dark matter. These valleys, carved by fluctuations from the Big Bang, became the highways along which matter gathered. Imagine a landscape where invisible rivers flow, but they carry gravity instead of water. Where these rivers converged, matter collected and galaxies formed. Where they stretched between nodes, long filaments appeared vast bridges of gas, dark matter, and young stars. Between these filaments, the spaces deepened into enormous empty basins, the cosmic voids. Light traced the structure. Darkness defined its scale. By now, the universe resembled a cosmic spiderweb, a three-dimensional network of brilliance and shadow. Every galaxy glowing inside a halo, every halo resting on a filament, every filament weaving through the night, every void expanding outward like the dark space between branches. This web wasn't just structure, it was destiny. It would guide the formation of every galaxy for the next 13 billion years. Filaments, the highways of light, The filaments were the busiest places in the universe. Here, gas flowed like invisible rivers, galaxies formed in clusters, star formation ran rampant, mergers happened frequently, black holes grew rapidly. Yet these regions were not crowded. They were still enormous tens or hundreds of millions of light years long. But compared to the voids, they were bustling cities of matter. Light from the first stars found company here. It bounced off gas clouds. It reflected off forming dust grains. It illuminated regions that had never known brightness before. The filaments were the first true glowing structures, beacons stretched across unimaginable distances by gravity's careful hand. Today, telescopes can still see these ancient filaments in the distribution of galaxies. They are the backbone of the cosmos, the illuminated veins of a universe that has just begun to breathe. Voids, the silent kingdoms between. If filaments were the highways of light, the voids were the kingdoms of silence. They stretched across space with impossible emptiness regions so deserted that galaxies could be millions of light years apart. In these voids, the darkness was pure, not polluted by starlight, not warmed by radiation, not shaped by turbulence, just stillness. A stillness so perfect that the nearest atom might be a football field away. A stillness so deep that a photon could travel 1 billion years without brushing against anything. This was not the darkness of the early universe, a darkness born from fog. This was the darkness of clarity, of emptiness sculpted by time. It was beautiful in a way few things can be, a vast, peaceful expanse that emphasized the brilliance of the filaments. Without these silent domains, the light of the filaments would have no contrast, no depth, no meaning. Darkness was the frame around every cosmic portrait. Galaxies grow in the web as hidden cradles. As the cosmic web matured, the densest nodes, the intersections of filaments, became the birthplaces of the earliest large galaxies. These nodes were cosmic crossroads. Matter flowed in from multiple filaments. Gas clouds collided. Star formation surged. Black holes grew rapidly. Clusters of galaxies began to assemble. The first galaxy clusters, small at first, formed in these dense nodes. But most galaxies did not live in clusters. They lived along the filaments, born from gentle flows of gas and turbulent pockets created by early supernovae. These galaxies varied widely. Some were simple disks, some were chaotic clouds, some were flat and thin like pancakes, some were lumpy and round like cosmic seeds. The diversity of galaxies was written into the structure of the web itself. Light followed the filaments followed dark matter, and everything followed gravity. The darkness that defines shape. It might seem strange, but the darkness between stars was just as critical as the stars themselves. Darkness determined where matter could move, how gas could flow, where galaxies could form, how clusters assembled, which regions remained lonely forever, where black holes would eventually grow. Darkness set the boundaries. Light filled the spaces in between. Every bright region owes its existence to the empty regions surrounding it. Without voids, galaxies would not form in clumps. They would be evenly spread, too diffuse to shine brightly. Without filaments, there would be no structure at all. Without dark matter, nothing would gather. Without hydrogens cooling in the dark, stars would struggle to ignite. Light and dark were locked in a partnership from the very beginning. They were not enemies, they were co-creators. The universe begins to look like it does today. By 700 to 900 million years after the Big Bang, the universe had matured. Not fully, not even close, but enough that its structure was recognizable. Galaxies grouped along filaments. Clusters formed where filaments met. Voids deepened between structures. Starlight travelled freely through space. Cosmic dust began to appear. Black holes grew more massive. Supernova enriched the filaments with heavier and heavier elements. The cosmic web was now illuminated by billions of stars, and yet the darkness still dominated. The void still stretched farther than the filaments. The shadows still outweighed the light. The emptiness still surpassed the fullness. The universe was a cathedral of contrast darkness as the towering walls, light as the stained glass windows, and both were needed to complete the structure. The cosmic web had taken shape. Light had emerged from the earliest stars. Darkness had stretched into vast, deep oceans. But the universe was still young, not even 1 billion years old. Everything that would one day exist still lay ahead. Galaxies with elegant spirals, planets wrapped in atmospheres, stars like the sun, black holes millions of times the mass of stars, and eventually life. Before any of that could happen, the universe needed one final ingredient: time. Time to settle, time to organize, time to refine the raw structures born from chaos and fire. This final stage of Chapter 5 explores how the universe used its enormous silence to craft the foundations of everything that would come. The deepening of the voids. As galaxies formed and collected along the filaments, the empty spaces between them, the voids continued to expand. Not because matter was removed from them, but because they collapsed less efficiently than the dense regions. Gravity is a sculptor of contrasts. It sharpens what is already heavy and softens what is already light. The voids were simply too empty to develop inward pull. While filaments became denser and clusters more crowded, the voids were stretched wider by cosmic expansion. These voids became the universe's silent kingdoms regions that would remain dark for billions upon billions of years. Some voids today span hundreds of millions of light years, almost entirely devoid of galaxies. They are the quietest places in all of existence, and they were born in this era. The filaments strengthened their grip. While the voids grew, the filaments rich in dark matter and hydrogen became ever more pronounced. Gas continued flowing along the filaments like rivers feeding a growing city. These rivers of matter brought fuel to young galaxies, allowing them to form generation after generation of stars. Each new star added light to the filaments. Each supernova created heavier elements. Each merger strengthened the flow of gas. Filaments were the highways along which the universe grew, and at the intersections of filaments, the densest node, something even more dramatic was beginning. The birth of the first massive structured galaxies. These would one day become giants like the Milky Way, Andromeda, and the massive elliptical galaxies in the cores of galaxy clusters. But in this early era, they were still infants, small, chaotic, and unrefined. Yet the blueprint was already there, the early appearance of supermassive black holes. In the hearts of young galaxies, something unexpected was happening. Black holes, some formed from the collapse of the earliest massive stars, began to accumulate matter rapidly. Gas spiraled toward them. Stars wandered too close and were torn apart. Dark matter deepened the surrounding gravitational wells. These early black holes grew at astonishing speeds, far faster than astrophysicists first believed possible. Some reached millions of solar masses in just a few 100 million years. These early supermassive black holes became anchors for galaxies, stabilizing their cores, shaping the flow of gas, controlling star formation, and creating new centers of gravity. Their presence was silent, invisible, but colossal. They were the hearts around which galaxies formed. The darkness begins to glow with order. As time passed, light no longer shone randomly from lone stars and chaotic clouds. It began to align, to gather, to organize. Galaxies developed shapes irregular at first, then more settled. Some became disks, some became spheroids, some grew spiral arms, some merged into massive ellipticals. Starlight filled the interiors of these evolving giants. Dust created by supernovae began absorbing blue light and re-emitting it as warm infrared, giving galaxies a soft glow that had never existed before. The darkness between stars was still vast, still dominant, but now it framed structures that were growing more intricate with each passing million years. The universe was weaving its first true patterns, the calm before a new transformation. By the end of this era, around 900 million to 1 billion years after the Big Bang, the universe had reached a delicate balance. Gas flowed along filaments, galaxies grew steadily, stars formed in waves, black holes expanded silently, supernovae enriched the cosmic medium, voids deepened and stretched outward. The darkness between stars, so vast it defied imagination, was no longer a barrier. It was part of the cosmic design. The night sky of this era was still mostly empty, far darker than anything we can imagine today. But when stars did appear, they shined with stunning clarity. Each point of light was a beacon of structure in a universe that had spent hundreds of millions of years learning how to create order from silence. But a new chapter was about to begin. The first stars had ignited. The first galaxies had formed. The cosmic web had taken shape. Now the universe was preparing for something even more transformative. The age of mature galaxies, the time when cosmic cities would grow into billion-star giants. This would be the era that set the stage for the Milky Way, for the Sun, for Earth, and eventually for life. The universe was just reaching its first billion years of age, a child compared to the 13.8 billion-year cosmos we know today. But already, deep transformations were taking place. The earliest stars had come and gone. The first black holes had formed. The cosmic web had revealed its filaments and voids. Galaxies had begun to flicker into existence like tiny embers in a vast night. Now came the next monumental chapter, the birth of the great galaxies. These were the galaxies that would one day grow into spirals, ellipticals, clusters, superclusters, gigantic cities of stars containing hundreds of billions of suns. The universe was about to take its scattered pieces and assemble them into the first long-lasting structures, the places where stars, planets, and life would one day emerge. And it all began quietly. What makes a galaxy? Great. Early galaxies were small and chaotic clumps of stars inside dark matter wells, shapeless clouds full of turbulence and motion. But great galaxies were different. A great galaxy is not defined by beauty or symmetry. It is defined by mass and stability. It is a system large enough to hold itself together against cosmic expansion, violent supernovae, and the chaotic flows of gas. A great galaxy has a deep well of dark matter, a central black hole that stabilizes its core, enough gas to form billions of stars, gravity strong enough to keep its stars bound, time millions of years to evolve. These giants did not appear instantly. They grew from the seeds of the earliest galaxies, merging, feeding, evolving. Over hundreds of millions of years, tiny star clusters collided and became dwarf galaxies. Dwarf galaxies merged and became larger spirals and ellipticals. These merged further and became the massive galaxies that anchor the universe today. It was a slow, elegant choreography gravity performing a dance across billions of light years. But before the great galaxies appeared, the universe needed something else fuel. The great inflows of gas. Along the filaments of the cosmic web, cold hydrogen rivers flowed into young galaxies. These inflows were enormous streams of gas stretching across millions of light years, feeding galaxies like arteries delivering nutrients to a growing body. Without these inflows, galaxies would have starved, unable to form new stars, unable to grow brighter. But the inflows were steady, powerful, and constant. They delivered hydrogen, fuel for stars, helium trace metals from early supernovae, cold plasma, dark matter momentum. These inflows created pressure differences, gas rushing into galaxies, colliding, compressing, cooling rapidly. When gas cools, gravity can grip it tightly, and when gravity grips gas tightly, stars form. Thus, the inflow of gas was the bloodstream of every growing galaxy. And as gas poured in from all directions, the first great galaxies began to swell. The birth of organized rotation. Before this era, galaxies were chaotic whirling clouds with no symmetry, no direction, no order. But as they grew larger, something remarkable happened. The gas began to rotate. At first, slowly, barely noticeable, but enough that gravity responded. Rotation stabilized the gas clouds. Stable gas formed disks. Disks formed stars in orderly lanes. Stars created structure. This was the beginning of spiral galaxies. The oldest spirals in the universe were messy, unrefined, but unmistakably different from the chaotic clumps before them. Rotation gave galaxies shape, orientation, momentum, stability. As the rotation became more defined, galactic disks expanded, swirling with billions of future stars. The cosmic cities had started to organize themselves, the invention of galactic centers. In the middle of these growing galaxies, something enormous was forming, a central gravitational hub. At first, this hub was just an exceptionally dense region of early stars, remnants of massive star clusters that had fallen into the galactic center. But soon, many of these dense hubs gave birth to the first supermassive black holes. Some had already formed from early stars, others grew by consuming gas falling toward the galactic core. Others merged during galactic collisions. These black holes didn't just sit there, they shaped everything. Their gravitational pull stabilized the galaxy's rotation, anchored billions of stars, forced gas into organized flows, controlled how rapidly stars formed, created the environment for spiral arms to grow. The earliest great galaxies were defined by their centers, hearts of unimaginable density that balanced the forces around them. Galactic hearts became the engines that guided the cosmic cities. Galactic collisions create bigger lights. Collisions between young galaxies were not destructive. They were creative. Every collision merged dark matter halos, combined gas clouds, triggered massive bursts of star formation, grew central black holes, increased rotational momentum, built larger and more stable structures. Instead of breaking galaxies, collisions made them stronger. The Milky Way itself is the product of countless ancient mergers, small galaxies swallowed over billions of years to create the giant disk we live inside today. During this era, collisions were frequent, and each one added a new layer to the growing cosmic cities. Light begets light, mass begets mass, and galaxies grew larger with every cosmic embrace. the universe begins to glow. Across the web, by 1.5 to 2 billion years, something extraordinary happened. The filaments began to glow, not because stars existed everywhere, but because the great galaxies, now bright and massive, illuminated the web with scattered sunlight. The cosmic web, once invisible, became faintly outlined by the light of galaxies strung across its threads. The universe was no longer a place of isolated sparks. It was a place of glowing clusters, swirling disks, star-forming nebulae, black hole-powered cores, galactic halos, supernova zones, bright city-like structures spread over hundreds of millions of light years. The era of cosmic cities had truly begun. The universe was becoming a landscape of luminous cities. Galaxies, once humble clusters of early stars, were now swelling, rotating, merging, and weaving themselves into the filaments of the cosmic web. Yet something deeper was happening beneath the glow, a process far more complex than stars simply appearing in the dark. Galaxies were learning how to build. They were developing internal rules, patterns, feedback cycles, and mechanisms that would govern their evolution for billions of years. In this part of Chapter 6, we explore the emergence of these internal architects, the forces, processes, and invisible hands that sculpted galaxies into organized, stable, and breathtaking structures. 1. The central black hole becomes a galactic architect. Deep in the heart of each growing galaxy sat a gravitational giant, a supermassive black hole with millions or even billions of solar masses. At first glance, it may seem strange to claim that something which consumes matter could build a galaxy. But these ancient black holes were not passive monsters. They were engines, stabilizers, regulators. Their influence extended far beyond their event horizons. How black holes shaped galaxies. They stabilized galactic rotation. Their immense gravity helped organize the swirling chaos of gas and stars into smooth, coherent disks. They regulated star formation. When gas fell toward the center, the black hole released jets and radiation that heated the surrounding gas. This prevented too many stars from forming too quickly. They sculpted galactic cores. Every galaxy needed a strong center to maintain structure. The black hole provided that anchor. They controlled galactic growth. If too much gas rushed inward, the black hole pushed back with enormous bursts of energy. This balance between gravity pulling in and black hole feedback pushing out was essential. It ensured that galaxies grew gradually, not explosively. Without these central giants, galaxies would collapse too quickly or fragment into chaotic clouds. Black holes were not simply destroyers, they were architects. 2. The first ordered star formation. Early star formation was frantic, massive population 3 stars igniting rapidly and dying violently. But now, inside the great galaxies, a new pattern emerged. Star formation became organized. How? Gas cooled along specific lanes. Rotation compressed material into disks. Gravity formed spiral structures. Cold regions collected into star clouds. Supernovae recycled gas and metals. Dust began shielding gas from radiation. The galaxy was developing a kind of internal logic. Star formation happened. In the densest parts of the disk, in spiral arms, in cold regions, shielded by dust in molecular clouds, in waves triggered by galactic rotation. This was the birth of the star-forming engine that would operate for billions of years. The great galaxies were learning to breathe, inhaling gas, exhaling stars. 3. Spiral arms. The universe learns geometry. One of the most beautiful structures in nature, the spiral arms of galaxies was beginning to emerge, not through artistic intention, but through physics. rotation density waves, gravitational pull, cooling gas star formation cycles. As galaxies rotated, regions of higher density formed like ripples in water. These ripples compressed gas, triggering waves of star formation in long, curved arcs. The result? Spiral arms, cosmic rivers of newly born stars. These arms were not solid structures. They were patterns waves moving through the galaxy. Like traffic jams moving along a highway, the cars don to stay in one place, but the jam itself holds shape. The universe was inventing geometry, symmetry, patterns. Galaxies were no longer shapeless. They were beginning to show elegance. 4. Supernovae become galactic recyclers. The earlier stars lived fast and died violently, but in this new era, their explosions served a purpose. Supernovae became the recycling engines of galaxy evolution. Each explosion injected heavy elements into the surrounding gas: carbon, oxygen, silicon, iron, shaped bubbles and cavities where new stars could form heated gas, preventing runaway star formation. Blew gas outward into the galaxy S halo, triggered star formation in neighbouring clouds. The death of each star became the birth of many more. Galaxies were learning a rhythm. Form stars, explode, enrich, form more stars. This cycle was the heartbeat of the growing galaxies. 5. The first dust grains appear. Dust. Tiny particles made from carbon, silicon and metal. Invisible to human eyes but vital to the universe. Dust grains cooled gas, shielded star-forming clouds and absorbed starlight. They were created in the explosions of early massive stars. Now, dust permeated the galactic disks, turning them into rich environments for building complex structures. With dust came the first nebulae, advanced cooling, more efficient star formation, the sculpting of spiral arms, the quiet birth of protoplanets, far later. The galaxies were gaining texture, layers, gradients, shadows. They were becoming worlds of their own. 6. The halos expand. Surrounding every galaxy was a halo, a massive sphere of dark matter, gas, dust, and ancient stars. These halos grew as galaxies grew, merging with smaller halos, absorbing stray matter, expanding through gravity, collecting gas blown outward by supernovae. The halo was the galaxy S atmosphere, a reservoir of material that would feed star formation for billions of years. Galaxies were becoming self-contained ecosystems. 7. The universe prepares for its first giants. By now, 1.5 to 2 billion years after the Big Bang, the foundations were laid. Rotational disks, spiral arms, massive halos, central black holes, organized star formation, structured cosmic web, enriched gas and dust. Galaxies were ready for the next step. They were ready to become giants. And soon, the universe would witness the rise of massive spirals, enormous elliptical galaxies, enormous galaxy clusters, quasars, black holes so bright they outshone entire galaxies. This was the dawn of the universe had laid its foundations. Galaxies had found their shapes, disks, bulges, spirals, halos. Black holes anchored their centers. Filaments fed them rivers of gas. Supernovae enriched their cores with metals and dust. Now the stage was set for something larger, something grander than anything the universe had ever constructed before. Galaxies were about to grow not just in number, but in size, mass, and power. This was the era when the cosmic web brightest nodes turned into colossal cities of stars, each one containing hundreds of billions of suns. This was the rise of the first giant galaxies. 1. Galactic cannibalism. Nature, its way of growing. Giants' galaxies are not gentle creatures. They do not respect boundaries. They do not avoid collisions. They merge. They consume. They grow by devouring their neighbours. This process is not violent in the way humans imagine violence. Stars in each galaxy are so far apart that when two galaxies collide, they pass through each other like ghosts. But their gas and dark matter and gravity do collide, and those interactions reshape galaxies completely. Every collision triggers massive bursts of star formation, violent compression of gas clouds, rapid feeding of central black holes, enormous supernova waves, a complete reorganization of structure. Small galaxies merge into bigger ones merge into giants merge into cosmic titans, and so, slowly and steadily, the first great galaxies rose from the ashes of thousands of smaller ones. The universe was building by combining its pieces. Gravity was the architect, collision was the tool. 2. The birth of elliptical galaxies. The titans of the early universe. Some of the first great galaxies did not become spirals. They became ellipticals. These were enormous, spherical or oval-shaped giants filled with old red stars. Why? Because elliptical galaxies were born from violent mergers. When two spiral galaxies collided at high speeds, their swirling disks shattered. Their ordered rotation broke apart. Their stars scattered into random orbits. The result was a huge, featureless, glowing sphere, a galaxy with no spiral arms, little cold gas, almost no dust, slow star formation, an aging population of stars, a supermassive black hole at its core. These galaxies were the giants of the early universe. Their sizes were staggering, hundreds of thousands of light years across, containing hundreds of billions of stars anchored by black holes weighing billions of solar masses. They were the first skyscrapers in the growing cosmic cities. While spirals were elegant, ellipticals were enormous cosmic megastructures built through raw collision. 3. The rise of the first true spiral galaxies. Not all galaxies collapsed into ellipticals. Many grew more gracefully, fed by gentle inflows of gas rotating in stable disks, forming stars in cool spiral arms, maintaining their angular momentum. These galaxies became the universe's first true spirals, the ancestors of later giants, like the Milky Way and Andromeda. The early spirals had glowing central bulges, thin rotating disks, dusty lanes of star-forming clouds, luminous spiral arms, powerful magnetic fields, enormous halos of dark matter, rapidly growing black holes. Their spiral arms were not permanent structures, they were waves, density ripples moving through the disk that triggered new star formation. Every wave created clusters, nebulae, massive stars, supernovae, and more dust. Spirals were engines of creativity. They produced new stars efficiently. They recycled gas perfectly. They balanced gravity and rotation with elegance and precision. These were the artistic galaxies, cosmic whirlwinds painted with billions of shining suns. 4. Quasars, the brightest beacons in the universe. As galaxies grew, so too did their central black holes, and at a certain point when enough gas fell inward, these black holes erupted into the brightest phenomena the universe had ever seen. Quasars. A quasar is a supermassive black hole feeding so violently that it outshines the entire galaxy around it. Gas spirals toward the black hole at nearly light speed. Friction heats it to millions of degrees. Jets erupt thousands of light years long. Light blasts through space with the power of 1 trillion suns. The earliest quasars appeared during this era within the first 1–2 billion years. They were visible across the entire observable universe. Their brilliance announced the locations of the massive galaxies that housed them. Quasars were lighthouses marking the cosmic web's most powerful intersections. 5. Giant galaxy clusters emerge. Individual galaxies grew, but they were not alone. Clusters began to form where multiple filaments converged. These clusters were enormous collections of hundreds or thousands of galaxies bound together by gravity. Inside them, galaxies collided endlessly. Black holes merged, gas heated to tens of millions of degrees. Enormous clouds stretched between galaxies. Dark matter sculpted the entire region. Clusters were the downtown cores of the cosmic cities. They were chaotic, energetic, overflowing with galactic traffic. And at their centres sat the largest galaxies of all supergiant ellipticals fed by endless mergers and cosmic flows. Clusters gave galaxies community. They gave the universe structure. They gave the cosmic web depth. 6. The universe shines as never before. By 2 to 3 billion years after the Big Bang, galaxies glowed brilliantly. Quasars lit the deep darkness. Star formation reached its peak. Galaxy clusters matured, spirals and ellipticals defined structure. Supernova enriched the cosmic medium. Dust filled the galactic disks, halos deepened and expanded. This was the brightest chapter in the history of the universe. The cosmic noon, the era when star formation was at its absolute peak. More stars formed in this era than at any other time. The universe had become a luminous ocean, galaxies shining like suns across unimaginable distances. But the story of the great galaxies was not finished. They would continue to grow, merge, evolve, and shape the cosmos for billions of years to come. And that journey carries us into the final part of Chapter 6. The young universe had changed beyond recognition. What began as a sea of cooling hydrogen, shaped by invisible dark matter lit by the first stars, was now bursting with creation. Galaxies had grown from tiny clusters into sprawling cosmic cities. Black holes had matured into gravitational titans. The cosmic web had deepened into a fully connected network of filaments and voids. But something more profound was unfolding, something that would define the universe's character for the next 10 billion years. The era of disorder was ending. The era of structure was beginning. This final part of Chapter 6 is the culmination of everything the universe had been building toward. The moment when galaxies became stable, mature, and truly magnificent. 1. The Great Transformation. From chaos to order. Early galaxies were wild. Chaotic clouds, ragged halos, violent supernova cycles, unstable disks, unpredictable collisions. But by now 2 to 3 billion years after the Big Bang, the chaos was settling. Galaxies had learned to regulate themselves. They organized into stable rotating disks, defined spiral arms, structured bulges, massive halos, interconnected clusters, peaceful voids. The galaxy was becoming a functioning, self-regulating ecosystem. It was no longer improvising. It had found a rhythm. Gas flowed along filaments in calm, controlled streams. Star formation happened in cycles instead of bursts. Black holes grew with measured precision. Galaxies, once crude clumps, were becoming architectural masterpieces, each one a city, each one a world, each one a story of gravity and time. 2. Spiral galaxies reached their prime rotation. The universe's quiet sculptor had finally done its work. Spiral galaxies emerged as some of the most beautiful objects in existence. They developed. Wide, glowing disks, luminous spiral arms, dusty star-forming lanes, central bulges, sweeping magnetic fields, massive halos of dark matter, elegant symmetry. Their structure was not static. It was alive. Every spiral arm was a wave, a ripple of density passing through the galactic disk and triggering waves of star formation in its wake. Blue stars lit the arms. Red giants glowed in the bulge. Clouds of hydrogen swirled like mist in a cosmic wind. The earlier spirals were still raw, thicker, clumpier than modern spirals, but their identity was unmistakable. They were the jewels of the universe, the places where new stars were born efficiently and beautifully. One day, billions of years later, a spiral galaxy called the Milky Way would host a small star named the Sun. But in this era, those spirals were just beginning. 3. Elliptical giants dominate the cosmic clusters. While spirals carved elegant patterns, ellipticals ruled with sheer size. They were born from the most violent mergers collisions so massive they erased all evidence of rotation. These galaxies became enormous, round or oval, filled with old stars, calm and stable, low in gas, prideful giants of the cosmic web. Their stars drifted in random orbits, a swarm of glowing embers filling enormous volumes of silent space. The centers of ellipticals often housed the most massive black holes in the universe, monsters millions or even billions of times the mass of the Sun. When several galaxies collided in a cluster's core, they fused into enormous ellipticals, some spanning 500,000 light-years. These giants would sit at the centers of galaxy clusters for billions of years, never moving far, anchoring the gravitational landscape around them. They were the cosmic mountains, immovable, majestic, ancient. 4. The cosmic noon, when the universe was brightest. If the universe had a golden age, an era of maximum brilliance, it was 2-3 billion years after the Big Bang. Astronomers call this moment cosmic noon. It was a time when star formation-peaked galaxies shined their brightest quasars, erupted across the cosmos. Black holes grew rapidly, metal enrichment accelerated, filaments glowed, clusters matured, the cosmic web reached clarity. The universe had never been brighter, had never been more dynamic, had never produced stars so rapidly. A single large galaxy could form thousands of stars a year. Gas clouds collided, disks spun faster, supernovae exploded constantly, black holes fed aggressively. This was the most productive, most luminous era in the universe's life. Everything was alive with energy. It was the universe's youth, a time of fire, glow, and ceaseless creation. 5. Galactic temperatures fall into balance. Inside these great galaxies, temperatures were becoming balanced. Hot gas filled the halos, glowed in X-rays, supported galactic clusters, resisted collapse, added pressure to the cosmic city. Cold gas filled spiral arms, cooled into molecular clouds, formed stars, created nebulae, fed central disks. The balance between hot and cold allowed galaxies to regulate themselves. Hot gas prevented collapse. Cold gas created stars. Winds from black holes prevented runaway growth. Dust cooled gas efficiently. Supernovae distributed metals. Galaxies became regulated systems, never collapsing completely, never exploding uncontrollably. This balance was the signature of mature cosmic architecture. 6. The first cosmic supercities. As galaxies grew and merged, some regions became true supercities, galaxy clusters connected by filaments and surrounded by voids. Inside these clusters, hundreds of galaxies orbited black holes, merged, hot gas pooled in massive halos, dark matter created colossal gravitational basins, stars formed in bursts, ellipticals dominated the core, spirals danced around the outskirts. Clusters became ecosystems, entire environments where galaxies interacted, fed from filaments and shaped one another's evolution. The largest clusters were like galaxies of galaxies, immense structures spanning millions of light years. These were the cosmic capitals. 7. The universe settles into its mature identity. By the end of this chapter, around 3 billion years after the Big Bang, the universe had become recognizable. The great structures were complete. Spirals with elegant arms, ellipticals with giant cores, dark matter halos, galaxy clusters, cosmic filaments, enormous voids, stable star formation cycles, regulated black holes, dust-filled disks, luminous quasars enriched interstellar gas. The universe had found its form. It had moved from chaos into architecture, from fire into order, from scattered clusters into structured webs. Galaxies had become the dominant actors, the cosmic cities that would host everything to come. Every star, every nebula, every planet, every ocean, every creature, every moment of life in the future universe. This chapter ends with the universe poised for its next transformation. The great galaxies are alive, they are stable, they are luminous, and soon deep within one spiral galaxy on the outskirts of a great cluster, a small star will one day be born. But that story belongs to another era.